All right. Well, it's a few minutes until noon where we're scheduled to begin our final day of the 2021 OpenVSP Workshop. Again, streamed online here through the OpenVSP Videos YouTube channel. Hopefully everyone can hear us online, and if not, I'm not sure how I would respond to you. I'll just type in, see if anybody can let me know if the audio is good out on the stream. So in the meantime, we're going to go ahead and talk one more time about how the presentations are going to go. You're welcome to go over to the OpenVSP Workshop main page for this year and share the links to the sessions. And for our viewers, just a reminder to bump your video quality up to 1080p so that you get the best resolution that you can through the player. And if you do want to follow along with some of these tutorials, we recommend that you watch the workshop on a separate screen and try and use your computer to follow along, because trying to do everything on one desktop gets a little tricky. And a reminder to everyone out there that if you have to step away for any reason, or if you couldn't make it today, those that are intending to catch it later, all of the sessions are going to be recorded and uploaded for viewing later, just like all our 2020 workshop videos. They will be segmented out and broken up by topic and by presentation, so no worries there. For our presenters today, which would be myself and Rob McDonald and Grady Pastor from Auburn, we'll mute the live YouTube stream audio while presenting just to make sure that we don't have any feedback, and maximize the presentations to get the best resolution that we can. If you do have audio on your computer to share, by all means choose include computer sound when you go to share content through Teams. And it looks like everybody is already present on the Teams meeting, so we can go ahead and move on from there. So reminder to our viewers, this is the page where you can go and find all our content for the workshop this year, and the link to our Conferences I.O. session where you can post questions and vote and poll on the ones that you want answered, or answer a few polls like where you're from, what types of demos or features you might like to see. Please go to this link and let us know. And we're watching that as well. That link is also pinned here at the top of the YouTube live chat, so you can find it there. In the technical schedule for today, we've got two short presentations from myself and Rob McDonald about OpenVSP Ground School and the projected area analysis, and then Grady Pastor will jump on and talk about propeller optimization in OpenVSP. And then Rob and I will be closing out the rest of the technical talks today with some demonstrations, more on the technical and the how-to side, and Rob will close with a tour of the OpenVSP source code. So this is not a repeat of how to build from source like was covered last year, nor is it an in-depth discussion of the API. This is more of a developer-centric presentation about where things belong in the code and how you would go about either modifying it or making improvements and doing things like pull requests to the get. Okay, well, with that in mind, we are right at about 12:01, so I'm going to queue up the next presentation, and we'll go ahead and get started. Go. All right, so Rob, can you see my screen? It looks like everything seems to be coming through. Okay, well, it seems like we're good to go. Again, I'm Brandon Litherland. I'm an aerospace engineer with NASA Langley Research Center in the Aeronautic Systems Analysis branch. And we're going to provide a quick update to the OpenVSP Ground School this morning. Generally what has been done over the last year or so, talk about some of the milestones and some things coming around the bend, and give you just a very short introduction as to what the ground school is if you've never heard of it before. And so it has always kind of been the case that OpenVSP is, of course, accessible and very intuitive to use, even to novice or inexperienced users and people completely unfamiliar with aerospace, in fact. And that was demonstrated just yesterday by Nat Breton, who picked it up and made an amazing custom component in a matter of 2 or 3 months. But the individual subtleties and the depth of the power of this software can take years and years to really get the hang of. And there has always kind of been a demand for comprehensive, multi-format, updatable tutorials that people can get to easily, understand quickly, and move on. And the unfortunate side is that a written document requires quite a lot of time to set up at the beginning, even in an automated fashion if we're trying to do things like generate docs from, say, the GitHub pages. And the OpenVSP core team and most of the power users simply don't have the time to do that right now, at least with not some dedicated effort. And so an online training program was deemed to be the best option, where we can make a series of how-to videos that can walk people through the basics and even advanced topics in OpenVSP in a natural way that would follow along how one would actually execute these steps. And the decision was made to follow that mostly because we intended to try and shorten the learning curve for the largest audience, and that is typically students, people completely unfamiliar with the software, or people that needed a reminder on how to do some specific thing without having to go in and read through a manual and find exactly what they needed to find. And so throughout this process, NASA's Transformational Tools and Technologies project has been generously supporting the work because it does provide guidance to our engineers and our graduates and our new hires on a tool that's very widely used at NASA. And the benefit of this is that because everything is open and published on our external facing sites, the public receives the benefit of this. And so the only things that the public doesn't see are the ones that have been isolated as either proprietary or not for release, and that can be kept on a different side. So what we decided was that some features of the ground school should be that it's easy to navigate, it's very intuitive, it lets you know where you are, and you can keep up to date with things. So not only does the interactive menu drop down and show you where you are in the training program by chapter, subject, and topic, but it also allows you to view our posts, get notified when new things are coming along, and it also has example files that you can use so that you can jump to a topic, execute the steps, understand the concept, and then pick up something else. So if you find anything that happens to be broken, or if something isn't working for you, please use the contact form for feedback and to ask questions. And the entire site is searchable by keyword or topic or category, so you can quickly find the topics that belong to what you're looking for. One of the things that we really wanted to focus in on was to make sure that the pages were responsive. So this works on monitors of any size, it works on tablets and smartphones and other devices. And every command within OpenVSP Ground School is intended to be active, meaning that you have to intend to do something. So the videos don't autoplay, it won't drop down a menu without you clicking the button. And that avoids not only the long press issue that is prevalent on some mobile devices, but it's also intended to be accessible to people of all ranges of physical ability. So some folks might use either visual or auditory commands to interact with their computers, and having a mouse button hover and accidentally activate a menu when that's not what was intended can be problematic. So we did our best to try and make sure that this would work well for everyone. So very briefly, we'll cover some updates and milestones. Around January of last year is when, or I guess January of this year, is when all of the Chapter 1 content was made public. So it was very short after the workshop last year. And everything in Chapter 1 ended up being over 150 tutorial topics in 19 fundamental subjects. And this is by far the largest group of content on the site. The other chapters will not be this big. We had to lay a good foundation so that everything else would make sense to you. And of course, all this stuff is searchable because you have the introductory paragraphs, you've got the video, you've got the categories and the hits. It will bring up what you're trying to search for. The Chapter 2 content is almost complete, so the production of the videos is effectively complete. We're just making the pages. And that covers things like design intent into your model with links, custom parameters, sets, subsurfaces, and the like. Just to let you know, we do have a final TQ milestone to wrap up the ground school content by the close of FY22, so in about 1 year. And that means that the baseline functional site is effectively complete, and you'll be able to find all of the stuff that was intended with the original release at the site, And everything beyond that point should be carrying out updates and maintaining the site and adding new features. So there shouldn't be a large continued effort beyond that point of trying to make some big contribution to a chapter, for example. The site has also been upgraded to WordPress 5, so you'll notice that some of the videos might play a little better on various browsers. It's all been bumped up to HTML5. And so what we had tried to do with forcing the player to go to 1080p, there's a reason that you don't necessarily want to do that because some folks' bandwidth might not handle that right out the gate. So we just allow you to select the quality that you want. And as far as minor updates and fixes, the subscription links, since the upgrade to WordPress 5, should work correctly and send out confirmation emails. So I've shown it to work on Gmail. It's apparently working on Outlook and Yahoo. And if that doesn't work, and I'll show you where that is, you can use the contact form and let us know that it's not working, and you can make a subscription request by another means. We've also updated the rounded rectangle and the wedge pages to update the changes. And all of the propeller introductory content is there as well. And so with that, I'm going to go ahead and escape out of this presentation and bring up the website. And I'll just show you a couple of things that have been added and show you where these things are. So give me just a moment here. And I'll bring this over. So when you go to the OpenVSP Ground School page, you're going to land on this main page, and then here we of course have our disclaimer that the content is being developed. We have links to the 2020 workshop recordings for all the subjects that we haven't got to yet. We'll also include the ones to this year's workshop. It'll give you a link to the Google group so you can ask specific questions there. And then you can track our posts. Now, if you want to be notified of any new updates, you can subscribe using this link. It'll take you to the form where you can put in your email address and it will send you a confirmation email. Or you can go to the contact form that's either here in the menu at all times or right here on the main page. So like I talked about, all of the navigation is here on the side. You can expand it out and take a look at, say, the introduction to the basic modeling process, where it walks you through building up a transport aircraft, and even going into things like details of individual cross-sections and the behaviors associated with those. And then we have links to various OpenVSP resources, including the old workshops, the Google group, the Hangar, etc. And of course, the example files that are all zipped up and ready to go so you can follow along if you want to. This is where you can find the search bar. If that's a bit inconvenient, just let me know. I'll add another one that's a bit easier to locate and to make it a bit more clear that that's available to you. And so while we're at it, let's pop over to the subscription page and I will show you where the piece has been updated. So here at the subscriptions page, we have a subscribe to widget where you should be able to just type in your email and click subscribe or unsubscribe to change your status. It should send out a confirmation email to that address and will only add you to the list after you've clicked subscribe. So it lets me track if there are unconfirmed requests out there, lets me send you reminders and things. If for whatever reason that does not work and that is still broken, you are more than welcome to use these two forms, and it's protected by CAPTCHA, so we try and get the bots out of our system. But just type your email address in, click submit. It will send me a request and I'll add you manually. Or if you don't want to be on the list anymore, type your email here and it will say that you want to unsubscribe from the list and I'll take care of it myself. So it seems like we've got just a couple of minutes here before Rob is scheduled to give his talk. That covers most of what I wanted to bring you up to speed on the ground school. Apparently some folks still aren't really aware that this has turned into one of the de facto sources for training and information for OpenVSP, and it's not really intended to replace discussions on file format or detailed guidance. This is more of a comprehensive list of how-to videos. So the stuff coming down the line here next will be things like VSP Aero and doing model analyses, and then we'll get into some more advanced stuff later. So as far as I can tell, I don't see any questions in either the live chat or the conferences IO. Rob, have you seen anything, or are you about ready to go then?
doubt anybody was timing their morning that they were going to join at the quarter after, but I don't see any questions for you.
All right. Well, if you like, I'll go ahead and stop sharing my screen on the Teams, and we can spend these 2 minutes or so to get everything set up here. You're welcome to go ahead and share your screen if you like, and you know, we're pretty close to 12:15 my time, where I think we might be able to just go ahead and roll.
Fair enough. Am I coming through?
I see your audio. The levels look pretty good here on the screen. If anybody out there is having trouble hearing, please let me know and I'll adjust those real time. But you're coming through on my end just fine. So I think you are welcome to proceed, Rob.
Actually, it looks like it's streaming the wrong screen. What did I tell you?
I see your calendar. Yeah, it did it again. Now I see your presenter view.
Good Lord.
Hooray, Microsoft. I can see a web page with the schedule on there now. There's me. Hi.
Okay. Well, you can see the word. You can see PowerPoint now, right?
No, I see my camera and I see the 2021 OpenVSP Workshop webpage. I can see your two open folders. And I can see PowerPoint now.
Okay, let's see if it lets me.
Nope, there's your calendar.
This is absolutely infuriating.
Yeah. Yeah, and I can see your presenter mode now. Oh, there we go.
Okay, we'll see if this does okay. I'm sorry, everybody, about all the technical troubles. It looks like we needed a couple minutes after all. This is Rob McDonald. I'll be talking about a short and sweet, pretty quick analysis feature compared to some of the others. This is the projected area tool, and we'll try and talk about some of the use cases if you're unfamiliar with why you might want to use it. The first use case is some aircraft or automotive things. Certainly, there are vehicles where drag or other quantities are computed or tabulated in terms of the frontal area of the vehicle. And so when you have a complex vehicle with, say, a body and a wing and other shapes, it can be tedious at best to calculate that projected frontal area. And so the first use case of this projected area tool is to be able to take a vehicle configuration like this one, and you can see this red area here. It'll compute that shape, the outline, and the area of the projected area for that vehicle. And to make that very easy, much like CompGeom calculates the wetted area very quickly and easily, projected area will calculate that frontal area very easily. Another use case is instead, for the rotorcraft world, they're often interested in the downwash area underneath the rotor. So in this case, what we've done is we're actually taking the area of the helicopter, the wing and the body here. We're taking its area shadowed or defined by the rotor, but also then normal to that rotor. So we're taking this vector of the normal vector to the rotor. We're projecting along that line to this body in the wing. We're using that circle as a trimming, and we're generating this red area down here. So this is that projected area of the blockage under the rotor. And so we calculate that shape, and then also its perimeter, the outline, and its area. And those are two of the main use cases for projected area. But anything else you want to do with projected area, it will obviously do just fine. The only tricky part about using this tool is there's a little bit of nomenclature that the GUI needs to have in order to support that complexity of those options that I just described. First, there's the direction along which you're projecting. That could be axis aligned, an arbitrary vector, or normal to a rotor disc. But so we'll have to specify the direction. There can sometimes be a boundary. So this is a region that we're going to clip this projection to, where we're assigning a boundary and only looking at the projection within that boundary. And in this case, that would be the boundary would be the disk itself. There's the target, which is all of the components that you want to project. So anything that you want to project is the target. And then of course the result is the answer. When you project this target subject to the boundary in this direction, you get this red area down here, which is our result. And as long as you understand the way I'm using these 4 words, then the GUI should be pretty simple and easy to use and self-explanatory. The first part of the GUI is where you can control the target. And here you can either choose a target set or a single geom as the target. And so in most cases, you'll have a set and you'll choose the group of components in that set to be the target. Then you have the boundary, which you can have none, that's unbounded. That would just get you the complete projected area. Or you can bound by a set, or you can bound by a single geometry. In our case, to produce this frontal projected area, of course, the boundary would be none. Then you choose the direction. You can either choose a vector made of x, y, and z components that you can manually set. You can simply choose the x, the y, the z vector, or you can choose a geom, which will find a normal vector on that geom and project along that. So you can choose the vector. In this case, for frontal area, we're going to just choose to do it in the x direction. Very simple. Your results are output to a file, which you can choose what the file is through the browser. And they're also output to this little window down here. The area is calculated and output here. And then, of course, we have the go button, the button that makes it all happen. You just click start, and it will run off and perform that calculation. Okay. Similarly, if you want to project along a vector in 3D space, we're going to change some of our options. We're going to change our set. We're projecting the helicopter. But now our boundary, we're going to choose a geom boundary, and it's going to be, the boundary is that disk. We're going to choose a direction, and we're going to choose it based on a geom, which again will be normal to that disk. And you can see that it goes ahead and it sets the sliders for that normal vector for us, where it's mostly in the z direction, negative z, so down, but a little bit tilted back because I did tilt that rotor disc back. We output a file, and I haven't hit the start button yet, but it'll calculate that area as soon as you do. And that's as simple as it is. I'll go ahead and do a quick demo if we can actually sort out which screen we're sharing and what's going on here. So, Brandon, can you tell me which screen is being shown?
Excuse me. Right now we have your 2021 workshop wiki page and the Teams window.
Great. Let me see if I can switch over and do this the way we want. Do you see my VSP screen now?
Yeah, I see the folder with VSP 25, and yep, I've got your window and the geom browser here in the screen.
Fabulous. Thanks, everybody. Okay, so we're going to replicate the case that was just shown. And so to do that, we need a pod to act as the role of that fuselage. And we'll increase its resolution just to make nice, pretty shapes here, and we can shade it. We'll add a wing, and we can drag that wing back. And this wing's probably too big for our purposes right here. So let's shrink that wing down. There we go, to more of a stub wing. Whoops, not that stubby. There we go, something like that. Maybe beef up the cord a little bit. There we go. So now we've got a wing and a body, and then we'll also add in a prop component that we're going to, for these purposes, we'll just use it in disk mode, and its design maybe here we go, a diameter of 5. We will rotate it 75 degrees in the Y so that you can see it's still tilted forward a bit. And then we'll move it back and we'll have it someplace located. Not in the Y. We'll have it located somewhere in the Z, somewhere over the vehicle. So there we have it. There we go. And we can shade that as well. And for fun, let's go ahead and increase its resolution so that we have a nice fine representation. So here we are. We have a representation of a rotorcraft. We have multiple components in a body. Let's go ahead and we can make that wing a little bit higher span so that part of it is inside and part of it's outside of that disc. And that's really our geometry. The next thing we need to do is to set up our set. And so we'll come down here to set 0 and we'll call that helicopter. And we'll choose that the wing and the pod are members of that set. And here we can choose the set to be the rotor if we like, and we can make that the prop. And so now you can likewise see if we come and look at our wing, and you look on the general, you'll see the wing is a member of the helicopter set, and so is the pod, and the prop is just a member of the rotor set. So we've got our sets all set, and we can come into analysis to projected area. And here's that GUI, as we said, and the simplest way to use it is first we'll choose what we're going to project. And if we just do shown, it'll also project our rotor disc. So we don't want that in this case. We just want to do the helicopter set. No boundary at first in the X direction. And if we just do that and we click start, you'll see we very quickly, it computes and triangulates this projected area, which we can then shade and click off of. And so you'll see we now have this component. And believe it or not, this is a mesh geom. So if we want to, we can actually export this as an STL file or a tri file or any of those triangulated file formats. You'll also notice that it has this boundary drawn around it. If we come over here and we turn off the mesh, it'll just show that boundary. So we have the ability to look at that. And if we do look at this file, which we can go look at real quick here, I think that's going to be right here. It's a CSV file. We can open that in Excel. Give that a moment to load. Here's that file. So you can see what it includes. It includes the date, the time, things that ran like that. Here's that area 2.27. The component areas, that's on a per component basis. So we have the wings projected area is this, whereas the pod's contribution was this. The component IDs that were in that set, here's the direction vector, the ID of what was created out. And then we have this path. And so the path is the 3D perimeter around the outside. And then we also have it projected into a 2D coordinates. So in this case, they're the same because we projected along an axis. But in a case where we had a tilted area, one of these will be just with 2 dimensions, and one will be a 3. And so that gives you the entire path around the outside of that shape. So that's what gets output, and all those results are available, of course, through the API if you're doing that kind of work. Just as a further example, we'll delete that mesh geom. We'll come in and we'll do the other kind of example where we want to trim, we want to set the boundary, and we're going to use the prop geom as our boundary. So we're going to use that disk. We will also choose a geom, and we'll choose that prop geom to give us that normal vector. You can see once again, it's mostly in the negative Z direction with a little bit of X. So we've done a sanity check on that. And again, we can hit start and it'll calculate that shape very, very quickly. We can do a show only on it if we want, and we can shade it. And what you can see is that we've trimmed that shape to that boundary. Now, you can see it's a little bit jagged here on the edge. If I show and do it as hidden, you'll see that that jaggedness is because we're actually projecting the wireframe exactly as you see it. So if I come in here and I were to increase, nope, not that one, but I were to increase my radial resolution and repeat the calculation, you'll see that this time with the show only, you'll see that I have much smoother curves here on the front and the back. And we've triangulated this mesh. Again, we can output it as an STL file if you want to. You'll notice that it's inclined. So in that CSV file, one perimeter will be here in 3D space going around in the incline, and the other will be rotated into 2D space that's normal to that direction. But again, the output area was calculated and that perimeter is also shown. And as you said, you can come in here and turn off the mesh if you just want to see the perimeter, or you can leave it on. And I think if you turn off the feature lines, it'll turn off that bold line around the outside. So that boundary is drawn as a feature line. And that's pretty much the entire story for projected areas. If there's any questions, I see one is about changing the color. So you can change where the color starts around a color wheel. And so you basically you can pick any hue around here as the best you can do for changing the color of a mesh. So hopefully that's sufficient. You can go pretty much anywhere you want here in terms of choosing that color. So if there's any other questions, I think that's all we have for projected areas. If anybody has more questions, type them in and I'll do my best to answer them. Thank you.
Thanks a lot, Rob. Appreciate the demonstration of that. I know that we've tried to include that one in prior workshops, but it's great to have it where we can record it and put it up for everybody to see. And up next, we've got Grady Pastor from Auburn, who has been working on propeller optimization in OpenVSP. And Grady, if you like, you're welcome to go ahead and share your screen, and we'll make sure that that's coming through okay.
All right, let me see.
Okay, we can see your PowerPoint window, and your presentation here looks good. So you are welcome to proceed whenever you're ready.
Okay, sounds good. My name is Grady Pastor. I'm a graduate research assistant in the Department of Aerospace Engineering at Auburn University. Today I'll be giving a talk on my master's thesis work, but more specifically today I'll be discussing the validation case, which uses OpenVSP and FlightStream for propeller optimization. So kind of the outline of what I'll be talking about, the actual propeller optimization itself, validating FlightStream, the source for the geometry, some of the data collection, which involves scanning the actual models and then processing that data. Then I will discuss the actual OpenVSP build for each of the models, and then exporting the mesh, and then finally the FlightStream validation. So the propeller optimization is for a variable pitch propeller using a real-coded genetic algorithm. The optimization scheme is built using Fortran and relies on FlightStream to provide accurate performance data for each propeller. The propeller is optimized based on efficiency and a user-specified thrust over 4 flight conditions. So the user will specify a takeoff condition, a cruise condition, 70% cruise speed, and then 110% cruise speed. These geometries are constructed using a Bernstein polynomial, which describes airfoil shape, twist, sweep, and chord lengths over the span of the propeller. Each propeller depends upon 67 parameters predicted by the GA to describe its geometry and adjusted pitch values for each of the 4 flight conditions. So we can see here the layout of how these parameters are distributed. So 24 parameters describe the airfoil surface, or the upper airfoil surface, 24 describe the lower surface. We then have 5 parameters for the chord, 5 for the twist, and 5 for the sweep. Then finally, there's 4 pitch angles at each of the flight conditions for a total of 67 parameters. So here's kind of the framework of the GA itself. So we have 128 members per generation with a total of 100 generations. The 4 fittest members are passed on to each generation, and they're passed to a mating pool, and this is where the next generation will be produced. This generation is produced by Laplace crossovers, single point crossovers, and uniform crossovers. This new generation then undergoes a series of power mutations in order to ensure a large amount of variance in each generation, and this is just to avoid any local maximums that would be run into. So the optimization is actually still a work in progress. So while the steady fixed solution has full boundary layer coupling modeled, the steady rotary solver in FlightStream does not have this feature yet. And you may have heard Vivek's talk yesterday where he went into more detail about this. However, though, the steady rotary solution does have separation markers that are provided, so we're relying on them for proper corrections to our propeller model. So you can see below, I ran the GA for a total of 4 populations with 10 generations in each one, and they all sort of converge on the same kind of clunky propeller. This is because a lower limit was set to the chord values to kind of avoid the problem of the flow separation. And so you can see here that the limit is set for this flow separation marker is set from 0 to 1.2. 0 indicates fully attached flow, and the 1 indicates fully separated flow. So you can see all these have, for the most part, attached flow. But as far as the correction goes, so I mentioned a lower limit set to the chord values. This was the first adjustment we made. However, this was kind of thrown out because it was more of an artificial adjustment to the GA and it limited the design space. And we also saw that the chord values met the lower limit within about 10 populations. So next we applied a correction factor to the actual thrust calculated by FlightStream. So this was kind of a penalty function. As more faces were seen by, or more faces saw detached flow, the thrust was decreased. And now we are trying directly including the amount of separation on the propeller into the fitness function. So we can output the actual number of faces that have the fully detached flow. And so if more than 20% of the faces see this fully detached flow, the propeller will be given a fitness of -10. And this is just to ensure that it will not be passed on to the next generation. And so this covers most of the propeller optimization, which I'll be talking about today, which is my master's thesis. So now I will move on to the actual validation for FlightStream. So the source for these validated propellers comes from the University of Illinois Propeller Database. This consists of 3 volumes that have propeller performance for nearly 140 propellers in low-speed wind tunnel tests. The data consists of a large variety of propellers from different manufacturers, and the propellers are relatively small and used mainly on small UAVs and model aircraft. And the performance data provides thrust and power coefficients for all propellers at given advance ratios. For this particular validation case, these advance ratios range from about 0.1 to 0.9, and the RPM values range from about 3,000 to 6,000. So the geometry data necessary to model a propeller inside the database is only provided for some of them, and even then it lacks information. So here are actually the 5 propellers chosen for this validation. They were obtained from volume 1 and consist of 5 different master air screw propellers. So we have an electric 11x7, an electric 9x6, Simtar 11x7, Simtar 9x5, and a GF 10x8. And so all these propellers are shown to the right of their names, and they should be scaled with respect to each other. So here's the data for the geometry that was provided by the UIUC database. You can see we were given radial values and then the corresponding chord and beta values in a table. And this was very easy to enter into OpenVSP. Because we could just go into the blade tab, select a radial value, and then type in the according chord and beta value. So notice though there is no airfoil data given, so we had to work around this by actually scanning the propellers. So airfoil data was gathered using a 3D scanner. We scanned the upper and lower surface of the propeller and then put the two together to provide the necessary information to reconstruct the airfoil in OpenVSP. So here you can see in the top image, this is actually one of the propellers that we scanned. Notice it's covered in this white film, and this is actually a raw image from the scanner. We actually had to cover it in this kind of, it was a painty, like a pasty kind of paint, so that the scanner could actually pick up the propeller. The scanner had a very difficult time picking up the original, the propeller was black, so the scanner couldn't get any light to reflect off of it. So when we painted it white, we're actually able to get a much clearer image of the propeller. And so here's the actual point cloud from that raw scan. This point cloud has been added to. So if you can look in the top image, you can see the trailing edge is sort of blended together with the surface behind it. And so when I was trimming these, originally I ran into an issue of trying to figure out where the trailing edge ended and the background started. So I had to add more points in MeshLab. And from there, I was able to easily define where to sort of stop trimming the propeller. So yeah, all these propellers were trimmed and cleaned up using MeshLab. And then, so actually here is the scanner we used. It's called the GoScan 20. It has an accuracy of 0.1 millimeters, volumetric accuracy of 0.3 millimeters per meter, and a scanning area of 380 by 380 millimeters with a depth field of 250 millimeters. So the scanner is shown on the left, and an image of the actual scans are shown on the right. So this is our setup. You can see these sort of clunky looking triangles shown where the center of them has 3 textured dots and the outsides or the points have these 3 colored dots. So the scanner needs at least 3 points of contact or to know where at least 3 points are at a given time in order to pick up new information. So we placed these blocks all around it for the scanner to keep track of them while it obtained information about the propeller. And so you can see the propeller here is shown with that same sort of white paint drawn on it. So after we scan these propellers and clean them up using the MeshLab, the point clouds were loaded into MATLAB and then oriented upon the appropriate axis. We just used PLY files for all these point clouds. The data for airflow sections were then, for the propeller, were then extracted and further altered to enter into OpenVSP. So all we did here, we have the top scan of the propeller in the upper image and the bottom scan of the propeller in the lower image. And so we just took cross sections at various sections to get these top curves and bottom curves. OpenVSP has the ability to use these airfoil files, these are just .af files, to model cross sections of propellers where the leading edge is 0, 0 and the trailing edge is 1, 0. So airfoil sections, after they were gathered from MATLAB, were rotated and translated such that the leading edge was located at 0, 0 and the trailing edge was at some point on the x-axis. These were then normalized by the chord length. So here, just a sanity check, we graphed one of the airfoil sections we gathered. So the top curve is shown with the blue dots, and the bottom curve is shown with the orange dots. And then on the right, you can see an example airfoil file. I will go into the format of this later on in my presentation. So a fuselage geometry, to start at least, the fuselage geometry was inserted and used to construct the actual hub of the propeller. So the length of the hub was set. This measurement was taken by a caliper. We didn't need to scan for this. It also gave us a good reference to make sure the scan geometry came out correctly. So then a total of 4 cross sections were used. The middle 2 cross sections were circles, and the first and last cross sections were points. So here in the design tab of our hub, we can see the length was set to 1.28 centimeters. And then in the cross section tab, we can see that the second cross section is a circle in type, and the diameter is 2.46 centimeters. So then we began with the propeller geometry. So we added the propeller by default in OpenVSP, and then 3 blades are added to a propeller when it is first introduced. So for all of our cases, the number of blades was set to 2. And then we move on to the actual cross-sectional data. So a total of 65 cross-sections were produced in the chordwise direction, and 45 cross-sections were produced in the spanwise direction. Generally, for lifting surfaces in flight stream, you need enough cross-sections in the chordwise direction to kind of capture the curvature necessary, and then the necessary amount of spanwise cross-sections to create a rectangle with the spanwise length of a cross-section equal to roughly 3 times the chord length of a cross-section. So you can see this, attempt at this down here at the bottom, where we have our chordwise cross-sections are 1/3 the spanwise. So, and then in the actual gen tab, we can see where we set the num-w and num-u to 45 and 65. So then we move on to the design tab. This is where the diameter, the number of blades, and the beta angle at 0.75 times the radius were set to the desired values. So all these models were built in centimeters. So this is 25.65 centimeters in diameter with the number of blades set to 2. And the beta angle at 75% of the radius was set to 16.69. Now we can move on to the actual blade tab for our geometry. The chord and twist were set using the geometry data provided by the UIUC database. This was very easy to implement. We would just go to the blade tab, we would come to the curve section and select chord or twist, and then we would insert values to split upon, and then insert the actual data that was provided by the database. So points were inserted at every 0.05 times the radius value. Next, we move on to the actual scan, where we implemented that into OpenVSP. So airfoil cross sections that were obtained with the scanner were implemented by using an AF file. This reads the X and Y coordinates of the airfoil. So the lines for the specified file are shown here. So you can see the file on the right and then the actual what each line does on the left. So the first line is our file type. That's just an airfoil file. Then the name, which is going to appear in OpenVSP when you load it in. So I chose to name this one 0.7439 times the radius, just so I knew where to load it in and which cross section went with which point. Then you can specify whether an airfoil is symmetric or not. In our case, we put a 0 because it is not symmetric. And then we'll specify the number of upper and lower points, and then we'll input the actual upper and lower points. So how we would do this is we come to our Choose tab, we would select AF file, then we would click on Read File, and then we would select the actual file which we want to implement at that cross section. 4 airfoil sections were implemented for each of the propellers. These were taken at roughly 20%, 40%, 75%, and 100% the radius for each propeller. Due to unreliable sections in the scans, these values actually were adjusted. So I believe this is for the GF 10x8 propeller. We actually had to use 18% and 74% instead of the 20 and 75% like we wanted. And this didn't have too much effect on the results. We just had to move them because either at that section it was very rough data, or I trimmed too much, or there was not enough points to actually get a clean propeller. And so these sections were just chosen because they exhibited the most change in the actual airfoil shape along the span of the propeller. Over here we see the actual final geometry for our, this is the GF 10x8 propeller. So on the far left we can see the wireframe being shown, where the propeller is given in blue and the hub is given in red. And then if we move to the right, we can see the shaded image. And then this is just rotated to show you the 3D view of the propeller. So once the propeller model has been completed, in the Analysis tab, we can select the CompGeom tool. And here the model is just converted to a solid meshed body. The half mesh can be obtained, and this just cuts the body down a plane of symmetry. And this is very useful for the steady solutions of FlightStream. However, for unsteady solutions, the entire mesh will need to be imported. So we ended up just doing the entire model. And as you can see, there aren't a ton of mesh faces to begin with. For each model, it's probably somewhere around 4,000 to 6,000 mesh faces, which is a very fast solution for FlightStream. So we left the entire geometry as is. But once you hit execute, you should get a geometry that looks something like this, go from something like this to look something like this, where it's just one body. Once the CompGeom tool was executed, the File tab was then selected to export the model. So all models were exported as stereolith files or STL files. In the STL options, the tagged multi-solid file was selected, and the STL file was then saved and imported into FlightStream. FlightStream is the tool used for this, a mid-fidelity tool with very short computational times because it's a surface vorticity solver. Solutions are provided on the order of minutes and then sometimes seconds. Generally for the steady solver, we can see our solutions in about seconds, and for the unsteady solver, it's usually somewhere on the order of minutes. So FlightStream uses surface vorticity sheets and vorticity-based loads for the propeller analysis. The solver can operate in steady and unsteady cases, as I mentioned before, and it can also operate with compressible or incompressible flows. So for all of these propellers, we used compressible flows to model them. The unsteady solver can also provide solutions for edgewise flight, as well as flight conditions where advance ratios are extremely low, such as hover. So here are 2 images from our steady rotary solver. We have the vorticity shown on the left, which ranges from -0.6 to +3. And we have the separation marker being shown on from 0 to 1. So again, 0 shows where the flow is completely attached, and 1 indicates a completely separated flow. Next, we can see our coefficient of pressure with respect to the reference velocity we have inserted, and this ranges from -1.5 to +1.2, and our velocity magnitude is shown on the right, ranging from 0 to 50 meters per second. Next, the unsteady solver is shown. You can see on the far left, this is after one time iteration of 0.0001 seconds. And then as we progress to the right, we can see the model work towards the number of iterations we gave it, and we almost get a full rotation by the end. Here are the actual solutions from FlightStream for each of the propellers. So on the y-axis, we have thrust coefficient, and on the x-axis, we have advance ratio, and on the far right of the screen, we'll actually have our propeller, which we are modeling. So in this case, we have the UIUC wind tunnel data, which is provided in blue triangles. We have the FlightStream data, which is provided in these orange circles, and that's for the steady data. And then FlightStream unsteady data is provided in the green squares. So the unsteady data and the steady data were both plotted here, just to make sure that the solutions would match up. And you can see that they're very near each other and actually match up almost exactly. And then both of them run right through kind of the scatter of the UIUC wind tunnel data. Next, we have the electric 11x7 propeller. And again, we can see the FlightStream did a very good job at predicting these values. So these values are actually for the steady rotary solver, and the rest of the values shown will be for the steady rotary solver. But you can see that FlightStream did a great job of predicting the expected values from the wind tunnel data. There's a slight overprediction as we get to these lower advance ratios, but that's expected for the unsteady solver. As I mentioned before, it doesn't account for flow separation on the back of the propeller. Again, electric 9x6 propeller, we see a little bit more of an overprediction at these lower advance ratios, and that can be attributed to this for the same reason. However, you can see the results start to match up as you get to about 0.4 to 0.5. The results start to line up with exactly what was expected of them. The same can be said for the Scimitar 9x5 with a little bit more of an overprediction until we get to about 0.5 in our advance ratio. This is likely due to uncertainty in the scan, but overall the trend was captured pretty well for this propeller by FlightStream. Lastly, we have our Scimitar 11x7 propeller. Again, a larger propeller, and this lined up with almost exactly what was expected from the wind tunnel data. You can see the FlightStream solution for the steady runs right through kind of the spread of the wind tunnel data provided by the University of Illinois. So there are two main sources for these discrepancies between FlightStream results and the wind tunnel data. The first is the geometry data produced by the scanner for smaller propellers. So like I said before, that scanner needs at least 3 points to know exactly where 3 points are before it can pick up many more points. And with the thin leading and trailing edges of the propeller, as we moved around with our scans, the scanner seemed to not really know where the leading edge seemed to start and stop. And the same goes for the trailing edge. So there is probably some unreliability in the airflow that was gathered for them. The second comes from the significant scatter in the wind tunnel data. So as you saw on the previous slides, that scatter was a pretty wide range. And actually, so we don't know exactly where it's going wrong with that. And then currently under investigation, as I mentioned before, is how much flow separation affects the lower advance ratio at thrust calculations. And that's something we're still working on with my master's thesis. With that, I'll take any questions.
Thanks, Grady. And, good work building up the models in VSP and demonstrating how you can run out to FlightStream. I don't see anybody popping in questions here in the live chat on YouTube. And
We'll give them just a second.
yeah, it takes a minute for that to catch up. You're right.
Grady, I don't know if you've seen this, but I wrote a project earlier this year. I wrote a MATLAB program to automatically parse all of the data in the UIUC database easily into memory. And so you might check that out. It's one of the things I'm sure you found about the UIUC data is it's somewhat inconsistent in terms of what information is available for what props and how it's formatted. So, and so if you want to do a comparison with a large number of props, obviously it's not going to make geometry data appear out of thin air or airfoil data appear that's not there. But for example, you might consider looking at if you wanted to, try an attempt of building these with less information, you might look at that MATLAB script that I put up on the file exchange and might play with that.
Okay, yeah, that sounds great.
We've had a question in the live chat pop up on the timeline for the optimization process completion. You said you were still working on it. Do you have a ballpark of when the optimization is expected to be complete?
So I actually just hit run this morning on the newest update we made to it. And so these run times take somewhere around a little over a day. So hopefully by then I'll be able to judge kind of better, but I'd say hopefully by the mid-November.
So do you guys have a hypothesis as to, what you expect to be better than, say, a traditional Atkins-Liebeck type propeller optimization? Or, what kind of an answer you expect to get different from a blade element derived propeller design?
Right, so hopefully we're trying to get the 3D geometry, which involves the actual airfoil shapes. We have, the optimizers that do just I guess, the thin blade. And this just, I guess, uses the 3D. And there's more inputs you can involve in this optimizer that I didn't actually mention here. But right now we're just getting extremely thin propellers, or at least the cord is extremely thin because of the viscous coupling effects. So we're just trying to work around that right now.
Okay.
We've got a couple more questions popping up in the feed, and it's kind of nice. We have a couple of minutes to actually get to a few of these. We've kind of been running up to the wire this week on some of them, but one is asking if the optimized propeller can be set up for a particular flight regime, such as cruise. So it seemed like you had 4 different flight regimes where it was trying to find the best of all of those scenarios. Does it do like a cruise optimized setup where you can more heavily weight the optimal solution towards one flight regime or another?
Yes, so you enter, so I guess 4 thrusts, 4 altitudes, and then 4 speeds, and then you enter the weights given to efficiency and the weights given to thrust. So right now I have it on a 1 to 10 kind of scale. So I'm giving the cruise efficiency a 10, the takeoff efficiency somewhere around like a 5, and then I'm making the thrusts somewhere around 8 because I want those to be matched pretty much exactly to what you input. So yes, there's a weight. So the fitness function for each one of these is a weighted average.
Awesome. Thanks.
So we've got a question about the availability of your thesis when you're finished, and I presume Auburn University will make it available online as a PDF once you're done. But then also a question about the surface mesh on these appears to be finer than other things they're experienced with FlightStream. Is this required, or do you think you could use a reduced tessellation?
You could definitely use a reduced tessellation. We were trying, or at least me, I originally thought that something was wrong with the tessellation when importing these. That's why we're getting like an over prediction of them. So for that particular model, I just increased it to kind of a ridiculous amount. It's a little high, yes. For these models, these giant propellers, it's much lower actually from optimization just to get faster run times.
Okay. And from my experience working with X57, I kind of feel your pain on the laser scans because we have had a similar series of challenges both with the high lift propeller blades and the cruise propeller blades because laser scans that are that accurate have a tendency to have a lot of noise, and trying to go through and find the mean path between all those points is no small challenge, and even writing that out to an airfoil file can be difficult. The nice thing I think about OpenVSP in particular is if you have that information and you can assemble it into a single say STL or tri mesh, you can bring that stuff in. And here in just a little bit, actually, it's kind of a nice segue. We'll talk about slicing these watertight meshes for cross-section identification. So that being said, you'd be able to go in, and if you understand what the family of airfoils happens to be for a certain propeller, you can use fit model and tweak the values and have it match to very high accuracy without having to go through something like a Colfan shape transformation or what have you to try and fix it. So depending on how noisy that data is, you might be able to get around some of those issues as well.
Okay.
Yeah, there's a lot of interesting challenges there that I think I love this kind of project for a master's student, and one of the fun things about this kind of project is a lot of the challenges end up being not where you expected them to be.
Right.
So, well, thank you very much. That was a really interesting presentation.
Yes, thank you.
Yep, thanks, Grady. So we've got just 2 or 3 minutes here before I start the next presentation. This next one, we're going to revisit a topic that was covered in the 2020 workshop very briefly. Rob had a little bit of time to talk about how to slice imported meshes or to slice meshes to do, say, a more accurate or an easier to use point cloud for for fit model. And unfortunately, we had very little time to go through it in detail and explain everything step by step. So I thought it was worth going back and having a record and a few slides of how to walk through this process, what the benefits are, and show how useful and easy it is to do. And then, so I'll go ahead and bring that presentation up. I know we've got 1 or 2 minutes here where we can kind of eyeball if there are any questions popping up in the chat or over here on the conferences IO. But allow me to move some of this stuff off and we'll get set up for the next one. Should be this one. Okay, that looks good. And I'll go ahead and do this. So, Rob, can you see my slides on the Teams meeting? It looks like it's going out okay to the live stream.
Yep.
Excellent. Okay. Let's see. Yep. All right. Everything looks pretty good. And okay. Well, we are close enough to 1 o'clock Eastern time, and we can probably go ahead and get going just in case some of this and the demonstration runs a bit long. Again, I'm Brandon Litherland from NASA Langley in the Aeronautic Systems Analysis branch. We're going to cover a bit about a demonstration and a step-by-step on how to slice an imported mesh for fit model. And so one of the things that you might wonder about, why would you do this at all? Why would you go through this process of recutting a mesh when it's already there? You have the points, and technically you can use fit model on any one of those. Yes, that's true. But sometimes when you're bringing in an imported mesh from, say, CAD as an STL or from a piece of, say, CFD gridding software or a laser scan for that matter, the mesh is likely to be unstructured. The points very rarely lie on a 2D planar section. And so matching cross sections closely to this distribution is difficult, but certainly not impossible, because you are allowed to select, say, a region of points in fit model. But capturing the ones that you really care about in a small enough slice is kind of tricky. So it's, I'll go ahead and say that trying to perform fit model with lots and lots of distributed targets, it works very rarely, particularly if you have, say, dozens of parameters that you're trying to vary to make the fit work and hundreds and hundreds of targets. It's a lot for fit model to handle, even though technically it should solve. But there is a better way. So for this example, we're going to walk through the X57 common model fuselage that I performed a CFD mesh on to intentionally make it unstructured, and then brought it back into VSP, and we'll give a bit of a demo here at the end as long as time permits. But the idea here is that you import the mesh that you want into OpenVSP, and here you can see this unstructured mesh. And the idea is not to immediately convert it into a point cloud. We want to do some stuff with this first. And so the trick is to go to Analysis and Planar Slice. And so you can choose your slices and bounds, as you can see over here. You can choose automatic. And again, like Rob talked about the other day when talking about planar slice and some of these other tools, it will automatically pick up on the tangencies at, say, the fore and aft end. You can choose your normal axis and X, Y, and Z, the number of slices, and effectively just hit go. Now, you want to make sure that when you're dealing with a particular mesh, you have a set or that mesh is the only thing shown. So if you have the mesh that you're wanting to slice and a VSP component or multiple meshes in there, it's going to slice all of them. So by all means, pay attention to the isolated set that you want, and then simply click Start. And so what will happen is that imported mesh gets sliced, and it ends up with all of these nice regular sections as you move from fore to aft. And they each have their own color ID, and they're each in their own location. And so the idea here is that you only want these slices, and the way that you can get that is to turn off the mesh radio button over here in the mesh geom. You'll go to the other tab and turn off mesh. Oh heavens, what's happened here? Rob, can you hear me on Teams?
I can on Teams.
Okay. All right. So the connection should be back now. I think my internet might have just caught a slow spot. Can everyone hear me online? It seems to be going out and the connection's good again. Um, Everything looks good as far as the stream quality. So I'm going to go ahead and roll. And if people can't hear me or if something seems wrong, let me know and I'll see what's going on. All right. Okay. All right, great. So in any case, we only want these slices to be used for our targets. So we, again, deactivate the mesh radio button and we want to only export shown. Now, what I discovered this morning and had to make a quick edit to the slides is that you apparently have to use this STL format. I did try it with Cart3D and it exported the skin as well as the slices every time I tried this. I'm not quite sure why it did that, but maybe it's a feature, maybe it's a bug, but STL does work. So the idea here is you export the STL, save it as whatever you want, and then as you bring this back, you just import that mesh, and now we can come over and convert it to a point cloud. Again, go to the other tab and click convert. You can see that all of these have the same ID, and it's still just the 2D slices. There is no outside mesh to this. And this is what results. So the points are only created on the outside of this mesh because that's where all of the points were. And now we have a nice ordered structure of two-dimensional cross-sections going all the way the length of this fuselage, which is really handy. It's really easy to isolate these and grab them for fit model. And so you can see here that this point cloud has all of the information built in here. And with this, we can go ahead and isolate what we need for fit model. We can choose our cross sections, and this is a much easier application in trying to manipulate, even by hand, into the points that you're trying to fit. And so this is a bit of a short, step-by-step process of the fit model where we identified one particular cross section, chose the 50% U cross section here, so it's 0, 1, cross section 2. And we set up fit model to attach only to that location and used all of these planar points right here. And because all of them were well defined, attached to this cross section, easy to attach, we just gave it all of the parameters that could define the shape and hit fit model. And sure enough, you get down to about 0.0001 distance metric because my tessellation in the W direction is pretty poor. So there are some gaps in here, of course. But it comes up with the shape that's intended very, very easily and very well. And so some tips and tricks here that you can use for guidance if you're trying to do this and even trying to isolate a particular slice. So if you're looking for a certain slice location, as Rob demonstrated last year, you can set the number of slices to 3, which is the minimum, and you can set the start and end equidistant from whatever location that you want. So for example, if you want to slice exactly at 9, start at 8, end at 10, and the middle section will be right at 9. But the nice thing is that the distance doesn't actually have to hit the model, so the first and last slice can be completely off of whatever it is that you're slicing. So if you choose plus and minus 100, assuming your model's less than 100 units long, it will end up with one slice in that geometry right where you wanted it to. So you only have one to deal with. If you're trying to get, say, the skinning just right, and you can do this in either Y plane or a Z plane, slice at Y equals 0 and repeat the process. And that's going to give you a slice of points that go straight down the center of your body. And if you happen to know that, say, a bulkhead or some section is at an odd angle within the geometry that's scanned or within the CAD, and you want to recapture that, you can rotate the mesh by that angle, slice in X, Y, or Z, and then rotate the result back, and everything will be oriented in the correct angle. So we actually got through that in about 8 minutes, which is kind of nice. So I can step through this in a demonstration to kind of show you what it looks like to go through this process. And I've got an example that helps us follow along with the X-57 fuselage. So based on the live chat, it looks like everything's still good. I genuinely don't know what happened to the stream quality there for a minute, so I do apologize about that hiccup. But I don't see any questions in Conferences IO or the live chat. So I'm going to pop out of this presentation and bring up VSP, and then we'll start with the demo. So we've got this here, give us a little bit more workspace to play with. And I'm going to come to my demos. So in this case, this is the geometry that we start with. So all I did was isolate the fuselage and run CFD mesh and get an unstructured triangulation of this surface. And so if we pop open a new model and we go to import, I'm going to bring in an STL. And in this case, it's just the X57 fuselage mesh. Let's say OK. And here we are. So again, that's that unstructured mesh that you saw. And just to show you why this is kind of a problem, let me come into the mesh geom. We'll go to other and we'll convert this into a point cloud. And we're going to show only. This is what that point cloud looks like all by itself. And, you know, the outer mold line is, of course, well defined, and there's points all over the place. And if you wanted to, yes, you can isolate these. So let's jump to, say, a left view. And let's go to our fit model. So all of these points are now available. And you can clearly see that there is one very clean 2D planar series of points here, but most of the rest have moved off. It seems my voice is cutting out from the stream too. I don't know what's going on with the quality right now. It might be that I'm trying to run a Teams presentation and stream at the same time. I might have to cut that out. Rob, if you don't mind, I'm going to go ahead and stop sharing my screen to the team and see if that works. All right, well, let's see how it goes. Anyway, so we can either select one or select multiple, or we can select a region. So if I wanted something up here, I could try and capture these points. Now you can see the problem already, that it's trying to catch near neighbors, it's trying to catch anything that we want to grab. But if we grab that, we think, okay, we've got all the points that we need. Let's turn that off so we can rotate. And what actually happened is it grabbed a whole bunch of stuff here on the right-hand side, and it missed a bunch of the ones that were behind it here on the right. It caught a bunch of stuff here on the left. But it's difficult to grab the points that you really want. You would have to rotate and grab, rotate and grab, rotate and grab. It's tedious, and trying to match a two-dimensional section to all of these and minimize the distance is going to be tricky. So let's see what happens if we do this a different way. Let's delete these points and go back here. And like I said in the demonstration, we go to planar slice. We'll give it, well, let's say somewhere in the neighborhood of 20 or so. We'll leave it automatic, and we'll start slicing. And now we have our slices, and it no-showed the original geometry. Here we've got our mesh and our slices. So if we turn mesh off, this is what we really want. And so now that that is shown, everything else is no-showed. We can come into File, Export, Shown Only, STL, just go with the default options here. And what that's going to do is we have our meshes. Now, this could be, you know, any number. Let's do slice mesh and replace this file. Hit accept. Okay. And now we can no-show this so we don't lose it. Go to import. Let's do an STL and slice mesh. So here are those points. Now, if we click on this, of course, the mesh itself is the surfaces. So if we shade this, that's what you can see. And what we want to do is convert that to a point cloud. So you click this button, and now we have our points along the outside of these slices. Again, let's go to show only, and that is what we want. This is a nice isolation of points into 2D sections that is very easy to use. So let's watch what happens here. I'm going to go back to that left-handed view, and just for fun, I'm going to go ahead and drop a stack into the model, and this is what we're going to use to play with. So I'm going to run to about, let's make it interesting. Let's come back here, try and match, say, this one. Bring it up in Z a little bit. All right, so that's a good place to start. Now, if I zoom in and I go back to fit model, I can go and select region, and notice that it's got points selected, or at least it thinks it's done. We are going to select none, have select region, and we're going to start highlighting these. And you can see that as I start to drag over and over again, it's adding more points to the number selected until you kind of know that you've captured them all. Now, if I look around, it's like, yep, caught everything that I wanted. And here's a little insight into fit model. You have to pre-select the geometry and the location before you hit add. So we want to fix this, in this case, to the 0.5 U location on the stack. We have our points selected, and now we'll hit add target. And all of them are free to go about W, so they're going to attach to the closest W position that they can on the surface, but they will go straight to U equals 0.5 at this cross section. Awesome. We've got our targets selected. Let's go to pick variables, and we're going to go in the cross section tab, and again come to cross section 2. Now, do not start adding variables until you know what type of cross section type you want. In this case, we're going to give it a general fuse, because if you change the cross section type, it's going to change the IDs of these parameters, and it's going to erase everything in the variable tree. But let's say we want to give it some delta X, Y, Z. We want to give it height and width to play with, maximum width location, leave the angles alone, but give it strengths to play with. All right, so we gave it plenty, but we have fewer degrees of freedom than the conditions. It's a well-posed problem. Now let's click fit. And well-posed problem, no problems whatsoever, snapped right to it, and we have a nice cross-section. So now if I press R and pick something to rotate around to have a better view, let me get rid of these so that we have a better view of this model. And you can see that this cross-section, near as makes no difference, lies right on top of that point cloud. And that is a much, much more reliable, much faster, easier way of getting to these cross-sections and getting your model to line up with the imported meshes. So it's a very powerful thing to do. And since we went ahead and did cross-sections in the X direction, let's take a look at what would happen if we, say for example, wanted to play around with the skinning. So I'm going to no-show this just so we can see what's going on. I'm going to hide this and go back to our original mesh. Rather than slicing in X this time, we are going to planar slice in Y, turn this off, and let's go from, say, -10 to 10, so that we only end up with one slice right down the middle. And we can do 3, and now slice. So there it is. If we come in here and turn off mesh, that's just what we wanted, a nice two-dimensional slice right down the middle of that fuselage. And we go through the same process. So we're going to export an STL of the shown components, and really it's just this Y equals 0 slice. So we're going to no-show, and we're going to come back to import, bring that STL in, and here we go. So we have this. Here's our Y0 slice. We convert to a point cloud, show only. So again, here is our nice, clean set of points, easy to follow, easy to fit model. And when you have multiple sections already defined, and let's say that you've matched the dimensions of each of the individual cross sections that you wanted to use, say 5 or 6 probably at most, now you can go in and start giving it skinning parameters to play with. And you can again select a region ahead of and after the cross sections and do these one at a time until you have almost perfectly matched the original intent of that geometry. Now I can come in, and what should happen if I open this, here we go. So this is the result of following that skinning operation. So I took a stack, I matched a few cross sections, and I matched the skinning using this procedure. And so what I want to do is, instead of import, I want to insert that fuselage geometry and take a look at how well we did. Now part of this is that this is still in inches, so we're just going to do 1/12 to bring that down to feet. And here we are. So if we select all and shade, Take our fuselage and change that to a nice transparent material, let's say medium glass. We look at it from the left, zoom in. The skinning matches exceptionally well. The cross sections are all defined very nicely. Everything is lining up, and we have effectively recreated this cross section. Now, something you'll notice is that the slew along in between these cross sections is very wavy. So if I come back to my stack geom here and go to a hidden view instead, you can see that it's kind of lofting that max W location around, and it's pulling and pushing and moving this it's moving this feature line away from where it would have been on the normal fuselage. That's going to be a byproduct of this process. You don't know where that should have been in the beginning, especially if you're coming in from something like CAD. So you do the best you can, and then down the road, if you need to tweak this a little bit where you know better than what Fit Model did, by all means, go in and change some stuff manually. That's fine. And you can clean it up and make it, as nice as you care to do it. So that is a demonstration of a few ways that you can use planar slice and meshes and Fit Model to try and recreate some of these geometries very, very effectively in a very short time. We're about 10 minutes ahead still, even with the demonstration. So I see Rob is answering some questions here. Was there anything popped up that I needed to demo, or how are we doing, Rob?
Sorry, I had myself muted. There's been some longer term demos that we might get to, but I thought I might, just for fun, give another example of what you just demonstrated. Let me see. I can see if I can pull something up here.
Yeah, let me go ahead and unshare my screen and minimize everything, and I'll bring you over. And you're welcome to share your screen when you're ready, Rob.
All right.
And we can see VSP, so you're ready to go.
So this is pretty impromptu, so apologies if I get it wrong. But the original version of what Brandon is talking about was when I actually made the original Tecnam fuselage that is now part of the X-57 model. And what we actually started with was nowhere near as nice as what Brandon was just looking at. This is the original STL file that we got from Tecnam as the company. And so you can see we've got really, nasty stuff all over the place. Nasty places in triangles. But if you'll notice carefully, notice it's not even well connected. Notice that we have here, if I change it back to wireframe, we actually have places where this sort of aft fuselage cone overlaps this next part because they were two separate parts in CAD, and they're both closed and they overlap, and none of these triangles match up. And this bulkhead is then at an angle. And we were sent this, glad to have it, very thankful to have it, but it was a mess. You can imagine trying to deal with this, where if you wanted to come in and try and fit one of these cross sections back here in the middle, there's absolutely no points back here to deal with. Meanwhile, yeah, there's a lot of points for this main bulkhead here and a good amount up and towards the front. But you can see that it's pretty chaotic where there's resolution and where there isn't. And so if you did the direct naive convert to points and look at it, you can see we've really got back here an odd assortment of points where it's just really unreliable if you want to come in and do a fit model. And then in particular, you've got spots here where we actually have, in the sort of normal to the surface of the aircraft, we have sort of different views on what that point should be. So we really have a giant mess. As a final example of that, if we view from the front, okay, we might be able to extract that center line, but even extracting that center line, it's still a big mess. And let's go ahead and just do that because I think it is instructive. So if we do a fit model, And we come in and we look at this and we just try and do by selecting a region where, we grab that and we grab it again. As Brandon said, we're adding to this. And the reason it has to happen this way is because the way OpenGL can do selection is based on coloring points. And so we can only select sort of the one in front. We can't really select all the way through in Z. So we can only select the one in front. And when we do this a few times, we're up to the 300 points now. We're hopefully, I'm not selecting the same region every time. So we're only adding one at a time there. So I'm going to do to hide all the unselected points and go back to being able to rotate in 3D. And you'll see I have now just pretty much just points along that side. But if I view left and do a full, you'll see that it's really sparse. I have this huge region back here, a long region on the fuselage where I have no information about what's happening along that part of the belly. And there's really very sparse information. And then I have this extra information that is because one of the CAD parts went inside the body and provided information that was not really just on the OML of the aircraft. And so while we were thrilled to have all this, like I said, it was kind of a hot mess of information. But we were able to, what I did was exactly what Brandon was just describing, was to come in and do something like, do a y-axis slice, start, come in, do that only. Oh, it turns out this is in different coordinates. So, I didn't change it to only 3, did I? Let me come back, change that down to, okay, just 3. And do it.
And we got to show our mess too. Yeah, there you go.
There we go. And so now if I come in, you'll see, and I can make that hidden, it'll help a little, that now I've really done a lot towards extracting it. Now in this case, because it was so many separate parts, and you'll see there were even some gaps in here, that we still had parts that were not, and we had some gaps up here in the front because these were not fully watertight components. You'll see that it's still not amazing. It's not as pretty as the case that Brandon was showing, but it's a big improvement towards extracting those points and just sort of decluttering your life, right? You can, instead of having to fight to select points along the center line, you can much more quickly de-res that model down and get it just to where you need it. So, Brandon's example is great. I use this trick all the time, but oftentimes in the real world, you don't have something as nice as that mesh he started with. The other case, let me see if I can find it on my hard drive. And who knows what we'll find here, but I did, here we go. And I'm just going to, here we go. So here's the original D8 wind tunnel model, or one of these fuse files. And you'll notice it's 482 megabytes. Think about that as a file that you're going to import into VSP. And so we're not going to do that, but first we'll choose the smaller one, which is only 98 megabytes. Let me copy this to my desktop and see if we can load it. So this is the other kind of thing that will happen commonly if you're doing fit model, is somebody will send you their structured or unstructured CFD mesh, which they've run a Navier-Stokes calculation for. And so they will have, it's a very lovely mesh and everything you could want, but it's also, 10 gazillion points. And in terms of fit model, it's just, what are you going to do with this, right? There's just too much information to deal with in a reasonable way. And so instead, you can just come in and do the same kind of trick where, by doing planar slice, we'll do it in the x-axis. We'll say we want, something like 11 slices. We'll do auto bounds, and we'll start slicing. And as soon as we do that, it takes a little longer because this is a pretty fine mesh. Um, we can, and actually, you know what? This may not have worked because we're not watertight on that original geometry. Um, yeah, so that doesn't work because the original was not watertight. I had to do some hacking to turn off that watertightness check in order to get things to work. But that's not a made for mainstream thing. If it's an important need, we can do that. I think actually the other file I have was watertight, so maybe I did it that way. But you get the idea that oftentimes you'll be given data, even if it's high quality data and not, with gaps and holes and overlaps. It'll be more data than you need, and just, you know, enormous files of ridiculously high resolution. And this technique can provide a nice way of downsampling that works really well as well.
Well, I appreciate the extended demo there, Rob, because it hammers home the point of why this is so useful and why people should have this in their back pocket. Particularly when you're trying to, do what you can with oftentimes very generously provided source data from either a manufacturer or university or from elsewhere. And like you said, we're really happy to have it, but there are things that you can do to make your life a lot easier. Um, so it's about 1:30 now, and our next presentation actually segues very nicely into what we were just talking about, because anybody that was kind of paying attention is we were doing effectively mesh operations like planar slice to a mesh. We weren't doing it to a VSP component. So keep that in mind while we start moving on to this other presentation, which is, talking about using negative components to do trimming operations. And this is kind of it really wouldn't be a VSP workshop if I didn't show you guys how to do something kind of stupid and difficult. But we'll roll with it anyway. Let me go ahead and start this. So double check that the stream is going out. Just a few seconds of delay as usual. There we go. And Rob, do you want me to share it in the Teams as well, or would you rather just follow along in the stream?
Up to you.
Okay, let's see if maybe leaving my screen share and my camera off in the Teams meeting will help with some of those bandwidth issues that we were having. Okay, well, in this presentation, we'll talk a bit about trimming components with negative volumes and leveraging some of that stuff that Rob was talking about on Wednesday, dealing with CompGeom and CFD mesh and negative trimming and the like, and show you some of the application that you can do with this. Again, I'm Brandon Litherland from NASA Langley in the Aeronautic Systems and Nasalis branch, and we'll go ahead and get started with this. And so as an outline of what we're going to discuss today, we're going to look at negative volume, what it is, why it might be useful, how OpenVSP leverages negative volume in its various operations, and talk about, some of the trimmed CAD export stuff like Justin talked about yesterday, and then providing some tips and guidance for things like conformal components in particular, because they have their own sort of behaviors and personalities when it comes to various components. And then we can talk a bit about some other guidance as well. So as an introduction to negative volume and trimming components, you can see that there are a variety of ways to create highly complex and in some cases detailed geometries for export or analysis, or even just for fun. So in the top left here, we've got an example of that split flow turbofan example model that I built up using prop components and some wrapped stacks, and I just sliced away a piece so you could get a nice internal view of that component. And in these others, here on the right side, this is a physical thickness watertight shell of an X57 high lift propeller spinner that includes the trimmed away region to allow the high lift blades to fold back into their recesses so that the blades can be conformal. And all of this stuff here was done in OpenVSP. I didn't use CAD to support any of this. You can make things that are additive and subtracted, where you can build up a complex component like this ball bearing in the middle or as radial bearing. And you can do things just for fun. So if you wanted to make a plastic, mace or something like that, you can make just, kind of off the wall, just for fun geometries, because why not? And the idea here is that you can add or subtract from OpenVSP geometries, from meshes. You can do this in multiple steps. And for those of you that kind of recognize what's going on here, we're effectively approaching Boolean operations where we're doing add, subtract, and union. So the idea here is that you can use this in kind of creative ways. So negative volume is again turned on under the general tab for all these components, and it's found here under the CFD mesh negative volume tab. You just turn the button on, and then rather than being an additive geometry where CompGeom or anything else will find the intersection and then use the outer surface and add it, it turns it around and uses the inside surface instead and just flips all the normals so that it's more of a subtractive geometry. And several VSP functions use this, including things like trim surfaces and CAD export, CompGeom and CFD mesh, and even mass properties and things like wave drag and planar slice, as we just demonstrated today and yesterday. And I guess, while I'm at it, this is what that VSP geometry looked like here in the top right. So these are these transparent red cutter volumes that I built outside the X57 high lift propellers as, say, envelopes for clearance. And then the result of that is the trimmed region here in these spinners. And I also hollowed it out using a conformal geometry so that this became a watertight shell. And one could 3D print this for fit checks if they wanted to. You don't have to use any other software aside from going to your printing programs. And so, again, the idea here is that you can trim away material from a model ahead of time, which reduces or even eliminates steps in your refinement later. And this can go for CFD gridding, going out to CAD, or again, 3D printing. So these are three different versions of that X57 nacelle, one of which was used for CFD analysis in a study on the conformal nature of the propellers and configurations. One is CAD for structures, and the other is a functional 3D printed model where these blades are hinged. There's a geared rotating connection down here at the bottom, so you can hand crank this up to speed and watch the blades deploy and get an idea of the dynamics of the system. So, this stuff is actually really useful. So we'll go a little bit into some techniques that will help you in this process. And of course, let's start with CompGeom because it's one of the most reliable ways to use negative volumes and do triangulated surfaces in VSP. And the guidance here is to follow the best practices that we've covered in the VSP Aero talks earlier, the CompGeom stuff, the intersection properties. Avoid poorly intersected surfaces and edges. And that includes, sharp angles and overlaps because you can end up with, say, infinite intersection, poorly defined edges. Just, use best practices there. And so the resulting trimmed surface is dependent on the surface resolution of the trimming component rather than the parent. So you see two examples of this down here at the bottom. On the left, we have a radial distribution of a fake cylinder that I put together, and it's only got two cross sections. And you can see that the resulting trim has all of these little needle or sliver triangulations inside the trim. So yes, this is a watertight surface, and yes, technically it can go to an analysis. It has surface area and everything else, but it's not great. So if you give it a few more points in U and make it so that it more closely matches between the two bodies, you're going to get a much better intersection. You're going to get a well-defined surface, and in general, it's going to be a better triangulation. So what we just talked about there is generally true for most functions that use triangulation rather than the Bezier curves themselves. And so just keep that in mind when you're trying to do things like this. And so kind of like we demonstrated it in the previous talk, is that CompGeom and most of these other mesh operations work on meshes too. So it goes for VSP generated or imported message from things like CAD or gridding or scans. So you can do these steps not only on native VSP components, but on things that you bring in or things that you create. So that if you look carefully at the general tab of a mesh geometry, you'll see that it has mass properties and it has the option for negative volume. So keep that in mind, that as long as this thing is watertight, it can have a volumetric density and it has mass. And so we're getting into the discussion here of Boolean operations where multiple addition and subtraction steps can be performed to create unique geometries in OpenVSP. So this example over here on the right, you can see that we started with that radial distribution of cylinders, and all I did was copy it, scale it down to about 98%, shift it a little so that it was aligned to the center, use that to core out the center, and then trimmed away fore and aft using two other box components. And the result is this kind of sheet metal-esque component that's kind of, you know, like a turning gear. And it is watertight. You can give it a density. You can do mass properties on this. You can do other stuff with these, which is really cool. I was kind of surprised when I found out how in-depth and how far down the rabbit hole you can go with some of these operations. And something interesting here is that if you find that the meshes aren't behaving well, you know, that the trimming isn't working improperly, you notice holes or gaps or the surface normals are flipped or VSP just outright crashes, you can export the multi-tag surface here that you can see all of these surfaces have different color. Export it as a tri or an STL and then bring it back in as a single mesh. That will usually fix the problem because it lets VSP kind of reanalyze where all the stuff is supposed to be pointing. So that will help you down the road. Some other things that you can do here, and because you can do this in a step-by-step process, you can use negative volume and export-import meshes to create custom features in a VSP Aero panel run. And so this was, you know, again, kind of just a fun demonstration to see if I could pull it off. But the imported meshes and the VSP components can be merged in panel mode. And so the quasi-Boolean operations here can be used to create flow-throughs and even things like fillets and strakes. So if you find that this, you know, build-up approach or this watertight mesh surface that you've built doesn't want to run in VSP Aero, you end up with that first iteration and it goes not a number and isn't happy or can't find trailing edges or something. Try turning on that experimental file format, kind of like we discussed with the best practices presentation. And you might find that it handles it okay. It just seems to be more reliable. So for the Strake example, I gave a talk at a workshop, I think like 2 years ago, where I had tried to make the inside of a fuselage component into a Strake by, you know, doing intersections and cutting things away. And so what I did here is I used that same component and I added some physical material for it to cut away from, and then I removed it. So over here on the right, you can see that what's left after doing that operation is what was intended with the fillet. So then it's up to me to try and get rid of all this other stuff and build it up on the bottom again, which can be done. You know, you can use the lower straight component that's involved in that, cut this away, and clear material out. But I found it kind of interesting that I went through the process of trying to piece all this stuff together and then bring it over into gridding software and then do the intersections and try and cut everything away by hand. And it was not a simple process. But to be able to do this type of stuff in OpenVSP, particularly if you're trying to do things like panel mode, it's hinting at some additional capabilities there that I hadn't really expected, which is really cool. So when we're moving on to things like CFD mesh techniques, you can of course adjust your lengths and your growth ratios to try and make sure that you have sufficient resolution of your tries. And as usual, avoid poorly overlapped surfaces, very sharp edges, and the like. And really, when it comes down to CFD mesh, you might find that there are some gaps, and that's kind of okay. If you're doing this to try and export out into CFD software for whatever reason, and you find that there are gaps in the tries, you can always repair that after the fact. This has done 99% of the work for you. You just need to repair some spots. So it's still good enough to go out, and the intersections are still there. And you can always make the primary mesh without the trimming, say in this unstructured CFD mesh, and then bring it back in and use negative volume to cut away afterward. And it should still work. So let's move on a bit to some of the things that go on in, say, the analyses in OpenVSP. And I always like to use these kind of nested spheres demonstration to show what's going on. So negative volume removes material in the mass property analysis because effectively it's just doing a series of planar slice. And so we have two examples here. One of example A, where it's kind of the old way of setting something to be hollow. You set an internal volume density to 0, and then you raise the priority so that OpenVSP knows that it's supposed to calculate that and then use whatever's around it as what's left. So once you do that, you can get the mass to come out correct, but the problem is it still thinks that it has volume. So in your mass properties, it's not cutting away anything. So if you look at the thickness here of about 0.1 length units, the mass comes out for both of these examples as 1.122. The volume of the first one is 4.16, and the volume in B is 1.122, like it's supposed to be. Because in the second one, negative volume doesn't need a priority or a density. It knows that it's not supposed to be there, so it just cores it out completely. So you get the right volume and the right mass, which is pretty handy. When we're talking about things like CAD export, Justin dove into this a little bit with the trimmed CAD example and showed that you can do negative volume and core things out. And the idea here is that you can get away with this. And the idea, particularly with trimmed export and trimmed CAD and negative volumes, is as long as what you are trying to export is a quality Bezier surface that's not going to cause problems, then it will come in as a watertight solid surface in CAD. So part of the issue of why you may want to do this, as opposed to trying to do some of these operations in CAD or to do things where you're, say, slicing cross sections of an exported geometry and then trying to loft that yourself, is that CAD lofting methods and OpenVSP's more fine controls in some cases using strengths and angles can differ quite a lot. So let's say, for example, that you have a geometry where you have a few cross sections and you're trying to loft all those together, but your options are either normal or tangential if you're trying to do a simplified blend, or you do a boundary blend using 3D curves to try and make everything go through. And yes, you have a lot of detailed control in CAD to make this exactly the way that it's supposed to be. But if you're in a hurry or you don't really care about those exact details, you just want something representative, or even worse, if you're trying to match something that exists somewhere else, that can be problematic. You can end up with ringing in the spline, you can end up with weird little over-tight curvatures, and there can be problems. And in fact, the lofting can often fail if sections with a different number of control points or regions, like I said, with very tight curvature are present. And so the idea here is that you would rather just export the true intended surface from OpenVSP and then modify things as needed. So if you wanted this example here where it's just a pod and a bunch of cylinders, cut everything away, and then say you wanted to round some corners in CAD to make it, not sharp. Let's say that this was a scribe or something where you wanted to be able to break off these individual little points at certain distances. Well, that's all well and good. You can finish that up in about 5 seconds in CAD. But the point here is that as long as you make sure that each component is capable of exporting cleanly, then you're going to have a good import coming into CAD. So quality part definitions in OpenVSP make intersection and trimming much easier in CAD. And so one example of this is the X57 folding blade hinge. And so what you might find is that if you export this geometry, say as a surface or even as a watertight solid, and you try and recreate it in CAD using slicing and then using, say, lofted surfaces without going through the process of making sure that the leading edge is correct, the tailing edge is correct, the top and bottom surfaces, the thicknesses are exactly right, that blend will oscillate up and down in between these cross sections. And to your eye, it might look fine, but if you actually get down into the details and measure it, it's different. And that stuff matters to structures, it matters to mass, it matters to your dynamics, it matters to your aerodynamics. All of that stuff does come into play. And so when you bring in the clean, smooth design from OpenVSP that doesn't have any of those features, and then say you want the reference location for, in this case, the folding hinge, you can bring that in along with the geometry that's already watertight. You've got a good, clean solid of the blade as it's intended, and then you can just modify the hinge mechanism for fabrication in CAD. So you can just add the features to a good surface without having to try and build the whole thing up from scratch and then eventually cause problems. And with that, we'll step in a little bit to some tips for conformal components. So quite often we'll see that if somebody wants to use negative volume for a conformal component, you're trying to make a shell, you're trying to hollow something out, you might even be trying to, make a void space for a fuel tank, for whatever reason, your application. It's a nice idea to try and match up the resolution in U and W between the conformal and the parent. So in one case here, you see in the top right, we've got a pod that has very low resolution, and the conformal has, say, num-W of like 41 or 21 or something like that. So you can see that it's very smooth. If you core that away, again, the trim surface is going to be based on the trimming component. So you're going to be highly faceted on the outside and then smooth on the inside. To have something that's more akin to a constant thickness shell, you want to try and match those up. And something that you may want to pay attention to is that something with excessively thin walls might have issues trimming for larger length units, like say feet or meters. If you're trying to get something that is a millimeter thick or even half a millimeter thick in some cases when you're trying to make something representative, say sheet metal, you might end up with some problems because the intersections, particularly if your surface and cutting resolutions aren't matched, you'll have one that pokes in and out of one another. Your intersections are not going to be well defined and you're going to end up with gaps. So be really careful when you're doing that. Or just scale into a different length unit is probably the better way to do it. Something interesting here is that the conformal num-U, num-W is only specified in one location, so it applies to each section of the child geometry, and that includes things like caps. So here in the bottom right, you can see that we have a conformal on a wing, and while the top surface has a num-U of 21, just like the parent wing, you can see that the caps also have a num-U of 21. If for whatever reason it is important to you that those grid spacings are relatively equivalent, just beware that that can happen, and you're probably going to have to go back and de-res some of those sections later on down the line. Some more behaviors of conformal components to watch out for, and this is mostly just, grid quality type stuff. It's not that this won't work, just pay attention to it. And that's that wing conformals can be a little bit troublesome when it comes to meshing, especially if you're doing things like UV or cord trimming. And it can cause the panels to kind of group and try and wrap around these edges. Now, it's still doing a great job. The conformal geometry, at least as far as the outer mold line goes, is doing exactly what it's supposed to do. But if you're doing this and you care about the underlying mesh on, say, the inside of this component, if you've got, say, CFD and you're trying to do sloshing or some crazy thing like that, you're going to have to deal with this and just know that exists. But something else that's kind of cool about conformals is they are a component that can be repositioned in the transform tab. So you can move their location, their rotation, and even their scale. And conformal components do not have to be aligned with the parent at all. In fact, if you make a conformal with a displacement of 0, you basically just made a clone of it. And you can offset it and put it somewhere else in space, and it's always going to track the outer mold line of the parent, which is kind of a neat little goofy way to use it. But in one of the recent releases, I think it was still around last year actually, conformal offset can be negative. And rather than creating something that fits inside the component, it creates an envelope around the parent instead. So in this view, we've taken this pod, set a negative conformal offset to something like, say, 0.1 feet. And what it's done is it's just kind of wrapped all the way around the outside. So if you wanted to have something that was a negative component to clear material away around some body and then mesh it, get rid of the pieces, and then add that other component back in, you can do that. That's perfectly fine. And something about conformal components that you really should watch out for is be careful using conformal with things that are really complex like propellers. There's a lot going on under the hood with that component. It is probably the most complex VSP component that there is right now. And when you try and put a conformal inside that thing, it's going to behave kind of like with the wing, but you're going to end up with some issues because it's trying to oscillate between the blade curves and make things match, and you're probably better off just building a new propeller with the parameters that you want. So just be really careful with that. Looks like I have about, 7 minutes or so until the end of this presentation. So let's talk a little bit about other guidance in this process. Don't try and do everything at once, please. You'll have much more success by trimming things away step by step or doing things one at a time. So subtract a little bit, add back what's important, trim a little bit more, and do these things step by step. So in some cases, you can have the negative component clear everything out and leave the pieces that you want, sure, but it's probably better to do things step by step, just like with VSP or just like with everything else. Excuse me. Build up complexity as you go. If you notice that your trimmed CAD is having some issues going into whatever software you have, try to determine what surface is causing the failure. And you can usually identify that by looking at it in a wireframe format. Most CAD packages will identify gaps and broken edges and poor quality BREP solids that come in and give you an idea of where the issue is. If that doesn't work, go, just like with VSP Aero and everything else, remove everything except what you know should come out nice and clean, export it, verify that it's good, and then add something else, and then slowly build the process back up and try and identify what caused the failure. And so we've got about 5 minutes here. I probably have some time for some Q&A, and while we're doing some Q&A, I might open a couple of these files just to show you what they look like in 3D, but I don't think I'll have time to go through the process itself because it can be a bit tedious. But I appreciate everybody's time and hope that you at least got something interesting out of it.
So Brandon, we had two questions that just came up. One was any suggestion on how you would use this feature to cut out a volume for a control surface or a flap for a wing that has a more complex geometry, any past experience? And then also, is it okay to make span-wise morphing wing? I think he means a blended wing with conformal components, and what's the best practice for it?
To both of those, I'll tell you what. Let me see what I can do here first. So here we go. Let's start with this one. Hopefully it'll bring in. So the answer to the first question is yes. You can absolutely use this feature to trim out components for something like a flap. And let me go ahead and select all here in shade, and we'll get an idea of what that looks like. And actually, perhaps a hidden view is more appropriate for this. But what I've done here is I've taken the clean X57 wing that's 2 sections, constant taper ratio, etc. I used a kind of a diagonal outer mold line envelope cutter on the flap and cleared that material away. And then what I did here is, you can come into the motion tab and change that from deployed to nested. And yes, you can clear material away from this and preset it up as ready to go for higher order CFD. Absolutely. What I will say is, unless you have done this very cleverly, panel mode is going to have kittens with this because you have vertical surfaces right here. If you're not very careful, it can refuse to acknowledge that this is actually an edge, and it will treat it like a blunt face. You can see you've got these really tiny points back here that probably aren't the best quality anyway. So I will say use with caution. I'm still developing some best practices on how to accomplish this, but it can be done. And particularly if you're trying to set something like this up for, say, RAND CFD or something a bit higher order than a potential code, you can totally do that. Yes. And let's see, is it okay to make span-wise morphing wing with conformal components? So for the morphing wing and the conformal components, I'm trying to make sure that I understand exactly what's being asked here. So with a conformal component,
Brandon, I'll demo that one in the next one when I demo blended wing.
Oh, okay, yes, because you've got your advanced wing demo. All right, well, yeah, that takes a little bit of the pressure off anyway. So appreciate that, Rob. But so yeah, there are a variety of applications here for using negative volume within your meshes. So you can certainly envision doing something like this for the simple case of a nested flap. Clearing out a region for ailerons is much easier. Especially if you don't really care about these things nesting, you can just take a box or something and cut that region out. And then let me just select all and show, and we'll show you what we're actually dealing with here under the hood. And no show this mesh. Oh, where's that other mesh? There's that cutter that I used. So we'll no show that as well. Here we go, and we'll no show that. So for Pete's sake, let me pick. There. No show that. And that. That's the clean wing. Anyway, so the X57 detailed model has these regions cut out in the airfoil files themselves. So Jeff Beacon from NASA Langley here in my branch as well made all the custom airfoil files that have the flap cove built into them. And, that's great for building up an outer mold line and for implementing these things in a physical sense. But you have to be really careful when you're doing stuff like this. So, yeah, there are a few ways to try and accomplish that. One of them is just trimming it away and then building up your grids and exporting out. Another one, of course, is directly modifying the airfoil files themselves. But you end up with these issues, right? You come back to the airfoil point and it needs to take a hard bend. Hopefully that is well defined, but you can have problems with that. So there are a number of ways to try and accomplish this. But anyway, so that brings us to 2 o'clock, and I will try and answer any other questions over here in the chat after I drop offline and let Rob go ahead and get started. But I appreciate the time to demonstrate this stuff. I know, I feel like I've got a reputation to keep that if I don't break something in OpenVSP, I'm not working hard enough. But Rob, I'll go ahead and minimize all my stuff over here, and you are welcome to go ahead and share your screen. We'll make sure that everything's set up properly.
Sounds great, Brandon. You're filling the role that Bill Fredericks originally carried, I think, well. And if you're an old Letterman fan, I think we could call this stupid VSP tricks.
Sounds like a winner to me.
Okay.
Yep, presentation looks good, Rob.
Great. Well, thank you guys for sticking with us. I'm Rob McDonald. I have a brief presentation here to talk about some of the more advanced features that you can do with modeling a wing. So I'm not going to be talking about the primary things of setting up a plan form, multiple sections, and adjusting the airfoil. We're going to go a little bit deeper into some of the other features in the other tabs on a wing to give some introduction into how all these things work. Specifically, we're going to talk about using the control surface subsurfaces. We're going to talk about mesh clustering on the wing, the section modification tab, and also wing blending. And this is an example of a wing that exhibits all of these things. You can't see the clustering because it's shaded, but it's clustered, it's blended, it's got control surfaces, and the trailing edge has been modified. So to start with, the work that was done to do advance the improvements to control surfaces, there's a few things here. What you have to realize is that a subsurface is drawn in the UV surface coordinates on the surface of a wing. And so what that means is that a straight line in UV space does not necessarily make a straight line in three-dimensional space. And so you'll often have cases where if you would build a control surface before we added some of these improvements that we're talking about, the front of the control surface would be curved in 3D space, but now we try and make it straighter, and it's not perfect. If you're to sight, you can see there's a little gap right here. If you sight along this line, you'll see there's a little bit of a wiggle, but we're doing better at trying to straighten out this line. So that's one of the things that's been done for control surfaces. In addition, we've got all these different parameters that allow us to control its position, its control surface dimensions, either in terms of fraction x over c or dimensional length in the dimension units of your model. And then things like being able to make the end angle, where originally here you'll notice that the control surface edge is aligned with the chord definition. Whereas here, it's actually making a right angle. It's making a 90-degree angle with the trailing edge, the edge that it meets up against. So we've got these different options to help model control surfaces and make them more realistic for subsurfaces. When you're working with a control surface, we draw the hinge line as we feed it to VSP Aero as this line that runs down the middle. And then we also show the direction of positive rotation from a VSP Aero standpoint. So here you can see that the right hand aileron positive is trailing edge down, whereas the left hand one is positive trailing edge up. And if you're ever unsure as to how this is going to go down, what you can also recognize is that these control surfaces all follow the right hand rule. So if you point your thumb along the hinge line, your fingers curl of your right hand, your fingers curl in the direction of positive rotation. And that's why you stick your thumb out the right hand wing, positive, your fingers curl trailing edge down. If you stick your thumb out the left hand wing, positive, your fingers curl trailing edge up. We have the ability to control some clustering, and we can do that both in the spanwise and the chordwise direction. And this is really easy to work with. The thing you need to understand is that the parameter is based on a fraction of the spacing if it had instead been uniform spacing. And the spacing is not done strictly in the chordwise along the chord line. It's actually done in an arc length along the surface. And so what you'll see is a 1.0 at the leading edge and a 1.0 at the trailing edge. We end up approximating as close as we can uniform arc length spacing, where every one of these panels has the same arc length along this airfoil from front to back. And so now when we control the clustering, it becomes a multiplier. How big is the first panel at the leading edge or at the trailing edge as a ratio to that uniform clustering? So at the trailing edge, if we make it a 2.0, you'll notice that this first panel is now twice as long as it was when it was a 1.0. And if we change it at the front to 0.1, this first panel is now 1/10 the length that it was originally. Or likewise, 0.25 and 0.25, we'll adjust those to be 1/4 at the leading and trailing edge. Now, in between, what we do is we use a hyperbolic tangent stretching function as of version 3.10. So that was kind of ancient history by now. But this hyperbolic tangent stretching function allows it to then smoothly figure out how to vary between these requests, to go and figure out how do I start at 0.25 and end at 0.25 and still fit the requested number of panels in here, and do that with as smooth and as elegantly a variation as possible. And this hyperbolic tangent stretching function is the exact same thing that's used in a lot of structured mesh generators, including Chimera grid tools. And so if you generate a structured surface mesh in VSP on a wing using clustering with these kinds of parameters, and you export that into something like Chimera grid tools, you get the exact same mesh as a surface mesh that you would get if you natively generated it in Chimera grid tools. So for things like that, it's just as good as using a lot of other tools down the road. Now, there's the Modify tab, and we may not have mentioned this yet here in the workshop, but a lot of GUIs you'll notice have many tabs or multiple tabs. And in general, kind of a rule of thumb when we design these GUIs is we put the most frequently used tab at the left, and as you go to the right, they become less and less frequently used, and they become a little bit more esoteric. And so as a user, you can generally know that sort of start with the tabs on the left, and if they're not capable of doing what you want, check out the next tab to the right and keep going. But for most usage, you'll never go all the way over here to the right. And that's just kind of a rule of thumb of how we try and design things to be intuitive in the user interface. So the last tab for the wing component is the section modification tab. And what it allows us to do is modify the airfoil. So the airfoil is specified in the airfoil tab, but what if there's something you want to do to mess around with it? And this just sort of happens. It's sort of a post-processing on the lofting of the wing where you set up your airfoil normally, and then you can change things. So the first part allows you to shift, rotate, and scale. And so this allows you to shift in X and Y. Again, these are in the airfoil's local X and Y coordinates. You can shift that airfoil section, you can rotate it, you can scale it bigger or smaller, and you can move that lofting where the leading edge is lofted on that surface. We can talk about some of the uses for this, but for example, one trick used for this is if you are trying to model a flap or an aileron, on a high lift wing in detail. What you can do is you can leave all of the wing's main section parameters, the aspect ratio, taper ratio, span. You can leave those alone. You can read in the airfoil section for your flap element, and then you can scale this element down. Say the flap is only 20% of the chord of the wing. You change scale to 0.2. And then you can use X over C, the delta X over C, to translate it back. To translate it back so that it starts where the flap starts. You can shift it down with Y, and you can rotate it with theta. And so you can use this to essentially position the flaps airfoil while still leaving the main wing parameters alone. And this is great so that you can have actually two wing components, one with, say, your cruise wing, and then one with your high lift element. And as long as those two have the same taper, sweep, span, aspect ratio, dihedral, right, all those parameters are the same, what you're going to get is this flap element, since you're sort of post-processing the high lift element in it using these modifications, it'll always match what that parent wing should be. And that's a neat way to try and add some of that detail if you need to. Another thing that we find is that airfoils are never the way you want them to be. In particular, a lot of mathematically derived airfoils may have perfectly sharp, razor sharp trailing edges. Or maybe they have a trailing edge that's not razor sharp, but for example, the NACA 4-digit airfoils actually have a trailing edge thickness of about, I think, 1% thick. Real airplanes all have slightly blunt trailing edges, right? We have manufacturing tolerances. You might have a piece of extrusion that makes up the trailing edge and it has a finite trailing edge thickness, or you might have a couple of pieces of sheet metal that come together. And so you have a non-zero, right? This is not the sharpened knife blade trailing edge. So you have a non-zero trailing edge thickness, but it's probably not the same thickness as that file was. It's probably not the 1% thick that the NACA airfoil came in. So one of the things that we frequently need to do is to come in and modify the trailing edge, to come in and say, you know what, we want to blunt its thickness, or we want to thicken that airfoil. And there's different ways of adjusting the thickness. Sometimes you thicken the whole foil. Sometimes you just cut off the trailing edge until you reach the thickness that you want. So these different techniques, sometimes you take a blunt trailing edge in a file, but you want to extrapolate it to a sharp trailing edge for a certain analysis code, like a panel code. And so that's really what all these different options are for, is how do you want to go about modifying that trailing edge so that your points match whatever your purpose is for your model. And in that process, we can also add a cap to the trailing edge. So I'll demonstrate what that is in a bit, but that cap can either be flat or rounded or cusped or pointed. So we've got some choices, and then we can control the parameterization of that. And once you understand sort of why you would want to modify these things, then I think most of the parameters will make sense. It's the confusing thing is people come to it and they don't understand why on earth this modify tab even exists. And it's really just confusing if you don't think about some of these use cases. Now, the blend tab of a wing is kind of like projected area in that it makes sense if we first start by talking about some nomenclature. We talk about how it works and why it works the way it does. So the first thing that you need to understand when we go to blend a wing is how this GUI is laid out and how it reflects a wing. So at the bottom here on the left, I've got a cartoon of a wing with two sections, and the sections then have airfoil 0, airfoil 1, and airfoil 2 going out the span. And if we think about controlling blending, we're always going to control blending at an airfoil. And when we start at airfoil 0 has an inboard side and an outboard side. And of course, the inboard side doesn't exist, so we've grayed it out. And so you can only control the outboard side. In the middle of a wing, say at section airfoil 1, we obviously have both an inboard and an outboard side. And so they're both going to be black. They're going to be available for us to work with. And what we're doing with blending is we're actually adjusting and modifying the leading edge curve and the trailing edge curve of the wing, either on the inboard side of a section or on the outboard side. And so you can think, okay, we've got this leading edge inboard, trailing edge inboard, leading edge outboard, and trailing edge outboard as 4 places where we can control the plan form of the wing in order to make a blended section. And that's exactly how the GUI here is set up on the right. Up at the top, we can choose which airfoil, and you can see that right now we're blending at airfoil 1. So we're on this middle section, and so both inboard and outboard should be dark. They should be black. There are options for us to work with. And then we have the top half of the remainder of the GUI is under this block here that says leading edge. And so it controls the leading edge line. And then below it, we have something that controls the trailing edge line. In addition to that, the left-hand side of both of these controls the inboard edge, and the right-hand side controls the outboard edge. And so this is sort of a matrix GUI where we're controlling what happens to that plan form line in each of these 4 quadrants relative to a given blend airfoil. So inboard, outboard, leading and trailing edge. And as long as you understand that, this should make a lot of sense. The next thing to think about is how we're modifying these edges. You notice right now it says free, 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 free. And what that means is we're just allowing them to be free to do what they want. They are unconstrained. And in this case, when you have unconstrained points that go from here to here, what that means is we're not applying any additional conditions. We're not telling it what to do. And so it's going to do the simplest possible thing, which is a straight line between those 2 points. What we can do is we can start to specify other constraints, other requirements. So for example, we can choose for them to be free, or we can choose what angle we want that leading edge to come off at. So instead of it finding a straight line, we can tell it, oh, I want to come off at 0 degrees, or I want to come off at 45 degrees. And that'll change that angle to match the constrained value. And what VSP will do is when you specify a constraint, it will then find what is the simplest curve that obeys your constraint that makes that leading edge or trailing edge modification happen. So you can manually specify the angle, or if you want, you can also tell it that you want to match the theoretical trapezoidal wing. And you'll see that over here on the right are the choices. We have free angles, and then we have in LE trap, in TE trap, out LE, out TE. So what this means is we're matching the inboard leading edge theoretical trapezoid wing, or the inboard trailing edge wing, or the outboard leading edge. And so what we're saying here is we want to match something for what that other condition would be if it wasn't blended. That's what I mean by the theoretical trapezoidal wing, or by trap here. It's sort of, we want to match the value of the straight line wing. And otherwise, if we want to match based on angles, then there's this option where it will basically create continuity. We can match on angles. And along with some of the other things in this GUI, anything that's not available because it simply doesn't make sense. For example, you're at section 0, so there is no inboard section. These inboard options will be grayed out. So an example, and I'll walk through this in a minute, but we're going to make a blended wing like the one that you saw on the first slide of this presentation. So the first thing to do in this case is to split a standard wing into 4 sections. And this is going to become sort of the body section, the main section of the wing, a transition, and then the winglet itself. And I haven't adjusted their span yet. I just chopped up this wing into 4 sections, and we'll know that then we're going to modify these into that plan form. And so then adjusting that's the next step. We adjust the chords so that they match what we want, and we adjust the spans so they have that inboard section, the main wing, the blend, and then that winglet. And for this case, the next thing to do is to make the dihedral what we want it to be. And there's two things that we need to do. We need to choose the option to rotate the foil to match dihedral. And that's important so that we have good airfoils coming through and we're getting a good airfoil on the tip of our winglet. And then in this case, we want to put half of our winglet angle in each. So if we want this to be a 90-degree winglet, we'd put 45 degrees at each, or maybe we'd put 40 degrees at each, and we'd have a slightly canted out winglet. But we're going to split that at the beginning and the end of our blend section. And so far, we're just setting it up for blending. We haven't done any blending yet. Next, we want to think about our design intent. And here I've flattened it back out just so we can talk about it. But you can see, for example, at one of these sections, we'll say at the intersection where the body meets the main wing, we want to leave the main wing as straight trailing edges, as a nice trapezoidal wing section. So what we want to do is we want to constrain this inboard leading edge. We want it to meet and match the outboard leading edge of the trapezoidal wing. We want to make that a continuity condition. We want to constrain that there. And we want to do the same thing. We want this inboard edge, we want it to meet here with smooth continuity. So we want to make that as constrained. And then we'll also say we want a blunt nose. We'll want to come to this nose and we'll want to specify the angle. If we want it to come off blunt, we'll say we want this to be a 90-degree angle. And so we'll specify 90 degrees and that tangency, and that'll start to build up what is our design intent. We'll do the same type of thing out here. But what we're doing is we're looking at each of these places and we're thinking about what do we want to happen? What is our design intent? Where do we want smooth blends? Where do we want to control the angle? Out here, we're going to want smooth blends on the blend section, but we want to leave the winglet itself as a trapezoidal wing and the main wing section is a trapezoidal wing. So all of our blending will be matching those theoretical trapezoidal wings at these joints. So once we've thought about this, then it's simply a matter of going through the GUI and setting all these constraints. So we're going to set, I said 90 degrees, I guess it's 0. So we set this leading edge angle at the root here. We set that to 0, and we do that at the trailing edge. We make this inboard section here, we make it match the outboard leading edge trap and the outboard trailing edge trap. Here at this corner, we match the outboard leading edge trap and the outboard trailing edge trap, and likewise here, the inboard leading and trailing edge trap. So we set that design intent, just following what we'd thought through. And when we do that, that starts to set the shape of the wing. And then finally, there's going to be, when we set those constraints, we get this nice blended wing, as long as we then have some adjustment. And the adjustment is the tangent strengths, which I'll show you in the live demo how those work. But once we've set that angle, we may need to come in and tweak some of the strengths to control how sharply it bends through these corners. But the result is we get these nice blends, and you can see this main wing section and the winglet section are both still straight trailing and leading edges, trapezoidal wing sections, but with really nice blends here between these corners and at these joints. And with that, I'll go ahead and I'll jump and do a demo of exactly the things we've just talked about. And Brandon, if anybody's shown any questions, you can send them to me on the fly. But I'm going to start here. I'm going to do a wing. In fact, I'm going to do it much like we just showed. I'm going to come in. I'm going to turn off the non-symmetrical side. We'll turn it back on in a minute. And I'm going to do no surface view so that we're just looking at the plan form. So it looks just like the tutorial on the screen of the presentation I did. I'm going to come into the section. I'm going to split it once, split it twice, come out to the outboard section and split it again. So now we're divided into those 4 sections that I talked about. Come to the inboard section, and I want to shorten that span down. So we'll make it have a span of 1, and maybe we'll increase that root chord some. So we'll thicken that up a bit, and we'll even increase its sweep a bit so that we've made some adjustments so that it is more like that root body. The next section out, that's going to be, let's say make that have a span of 6. That's going to be most of our wing. And we'll make the tip chord, we'll reduce that down to 1. So that's most of our wing. Our transition, that's going to be very small. Let's make it only have a span of 0.25. And for now, we'll make its root chord and its tip chord both be 1. We'll make some fine adjustments on that later. And then we'll come out here to the tip and we'll say we want that to be the winglet will have a height of 1 eventually, and the tip chord, let's make that about a 0.6. So we've just gone through and we've set our main plan form type variables, what we want them to look like. And here, let me rotate it so that we're looking at a front view. And next we're going to come in and I want to set our dihedral. So we're here, we need to rotate foil to match dihedral, and let's put in, say, that 40 degrees, and we'll do it all in a relative sense. That way they're cumulative. And so we'll go to the next one and we'll add another 40 degrees there. So now we've got our 80 degrees on the winglet with it broken in two. And that's a pretty good, nice, smooth way to make a winglet. And that's all we have to do for our main plan form. We've got something that roughly is looking like our wing ought to look. Next thing we want to do, we'll come back to a top view for this, is we want to adjust our blending. So we're at the root section, we're at airfoil 0. You can see we're highlighted in blue. And remember here, the inboard side, there is no inboard side to the root. So all that's grayed out. And everything right now is free, which is why we're getting these straight lines. So at the leading edge, so this top right GUI, we want to specify an angle, and it initializes it to the values that were already there. So we make no change initially, but we said that we wanted to make that a blunt straight line. So we changed that angle to 0, and we're not going to change the dihedral angle or the strength right now. The trailing edge, we're also going to control the angle, and we're going to set it to 0. So we've just set so that we're coming off square for those two. Again, we'll come back and we'll adjust strength later if we need to. Now I'm going to go to the next airfoil out. So now we're on this airfoil. It's highlighted in blue. And again, we want to change, we want to constrain this inboard leading edge. So we come to this upper left-hand GUI where we're on the inboard leading edge part. And we want to match, right now it's unspecified, so it's doing the simplest thing. But now we want to match, and we could specify an angle, right? We could come in here and we could set that angle to anything we want, right? We could control that angle anywhere we want. And that ringing you just saw, that was because the strength was not set well. So don't worry about that just yet. But we don't actually want to set this angle manually. We want it to match this line on the outboard side. That way we get a smooth transition to this trapezoidal wing. So we want it to match the outboard leading edge trapezoidal wing. So we'll choose that, and you'll see that it just set that to be a nice smooth transition. We'll do the same thing at the trailing edge. We'll match it to the outboard trailing edge trapezoidal wing. And we get that nice smooth transition. Now again, we've got this ringing here because our strengths are not in good shape. Here it's got a strength of 3, which is very strong here at the root. Whereas if we come to the inside side, it's got a strength of 1. So the first thing I'm going to do is I'm just going to change that strength back to 1 on both of these. And at least for now, that'll at least get it tamed back down. But we may want to come in later and change these two strengths relative to one another to get that curve to behave the way we want. Right now, I'm more interested in getting the rest of this blend working. So next, I'll move to the next outboard section. Here we are at the outboard part of the main part of the wing. And again, so the inboard side, we don't want to do anything. We want to leave that alone. But the outboard side, we want to match the inboard leading edge trap and the inboard trailing edge trap. So we just match those blends. It's hard to see much happen here, but if I rotate and I come in, you'll see that we've already started blending because we're now coming here and we're also smooth in the dihedral direction, right? Before, let me turn this off again. You'll see that these are jumping up as straight lines. And so when I change that to match the outboard leading edge trap and the outboard trailing edge trap, You're right. Inboard leading edge. And thank you. There we go, inboard trailing edge strap. You'll see that we're matching these both in sort of the planform, the sweep direction, but also in the sort of the dehedral direction. This line is a continuation that comes on up, but we're still meeting here with a corner because we haven't specified anything here. So the final thing we need to specify is come out to the next airfoil. Here we want to constrain the inboard side. We want it to match the outboard side. So this is the outboard leading edge and the outboard trailing edge side. So we match those up. And we've got a nice blend. And you can't really necessarily appreciate it entirely in line form. So let's come in here. We can change it back to a hidden or a wire. I'm going to increase the tessellation just so that it's nice and smooth. I'm going to come into each section, and right now I'm just going to increase each of these up to a pretty large number, perhaps excessive, so that we have it nice and smooth. And then if I do a shaded view, you'll see that we have nice blends. And in fact, if we change it to something with a little bit more sheen to it, like ruby, you can really see that we've got some really lovely surfaces and some really nice blends going on in these things. And even here, you know, in this blend, we've got really nice surfaces. And one of the things I really like about this is, of course, while we focused on getting on just getting very quickly to this point, now that we've specified design intent, right, we didn't have to dictate a whole lot of parameters to make this happen. It's really flowing from the design intent of the trapezoidal wing. So for example, if we wanted to come in and nuance the design of this winglet, we can come in and we're controlling the outboard section. And actually, let me, there's two things we can do. But first, if we twist this section, let's say we add some toe in, we had 10 degrees of toe in, you'll see that that toe in, you know, it slightly changed this angle down here, but it kept everything nice and smoothly blended. But we can also, of course, twist the root of that section. And so, you know, we have the ability here that we can twist the root and the tip, or we can come in here and change one of these airfoils so that it has, you know, we'll have some camber. We can invert the airfoil so that it's negative camber in this case, so that we have a flatter inside side, and we can twist and tailor the lift distribution on the winglet as well as the wing, and we're not having to really mess around too much with the details of that blend. I'm running a little bit over time. My next talk is me too, so I promised a little bit on some airfoil modifications and also conformal. So let me quickly just add a conformal component to this. And of course, one thing you pretty much always want to do when you're working with conformal is set the parent so that it's transparent. And we'll shade the inside one, and let's make it something pretty like jade. And so here you'll see that we have a conformal component of this wing, and we probably wouldn't want a fuselage that goes up through the winglet. So we'll come in here and we'll trim in U, and we'll bring this Umax way down. So let's say that we just had a cargo bay on the interior part, and we're going to trim in chord from say 0.2 to 0.8, something like that. And so here we've been able to come in and pretty quickly set up, and we can do a show only on that, where we've, you know, been able to come in and build say an equipment bay or a fuel bay from a blended wing, and trim it down and even through those blends. So that does work in to some extent. Let me delete that real quick so that we can come in, and I'll just look at modifying the root airfoil section. Here you'll see that this airfoil, it's a NACA airfoil, and we by default modify them to be perfectly sharp. You'll notice that there's an option here to sharpen the TE. So the formal NACA definition, as I said, it's like 1% thick, I think. So if you turn that sharpen off, this is now the NACA official definition with that 1% thick sharpness. But you know, who really wants that? So now you can come into the trailing edge, and we can modify its closure. and say the easiest way to do that is to skew, which is adjust both the top and the bottom. And we can do that in a absolute as a fraction of a chord. So we're basically 1% of the chord thickness, or we could do it in a relative way. Or I'm sorry, we're less than that. We're 0.2% thickness. So if we change that to 0, you can see we're just going to thin that airfoil back up. So we thickened that up. But you could also, again, if you had something where you knew you had a 5% thick trailing edge, which is a lot, but it exemplifies what we're talking about, we can thicken that airfoil to do that. The cap types, as we said, there's numerous types where we can round that over. If you come to the plan form, there's the cap tessellation to adjust how smoothly we draw that. So we can do round, we can do sort of a pointed edge or what's called sharp. And then these parameters control how that shape comes off. So if we have a strength of say 1 on sharp, what that's going to do is that's essentially going to be elliptical. It's going to meet this smoothly and come out. And you can offset it vertically up or down. So if you offset that to 0 or to 0.5, if you offset it to 0.5, you'll see we're going to match this top line coming off as a straight extrapolation, and all of the cap will be curved on the bottom. And that's the same type of behavior for edge, except with straight lines or with round. And that's a little silly because now we're rounding it and coming up and around, but you get the idea that we've got these ability to control this. Finally, I mentioned, the deltas, the thetas, and the scales. So, you can do that. You can translate that one section back. You could scale it way down, and you could rotate it in theta. And so, by adjusting that appropriately, if you were to go and do this across a wing, again, this is still positioned using that same plan form, the section sweep and things like that. But you could use that to position a high lift foil. And you can also, of course, change its section so that this section, if your main wing was a 6 series, you could bring in and change the section type so that you have a different airfoil for your high lift than you have for your wing. And I think that's everything. I've gone about 5 minutes over. I apologize for that. I'll go ahead and transition to the last pitch. Brandon, if there's any questions, I can answer them on the fly.
No, no pointed questions about the blending wing, and thanks for taking the time to walk some people through that. I know that it was a very desired feature back in the day, and seeing it demonstrated is really useful to the community. We have a couple of people that have chatted in that said that the blending feature in particular was really great, and it's part of the reason that they picked up VSP in the first place. So glad to hear that something so useful is bringing new people in. But
Well,
I'd say we've got plenty of time for our next presentation as well.
great. Well, thanks a lot. I appreciate those comments. When I implemented blended wing, it seems like it was a long time ago now, but I actually implemented it 3 or 4 times before it was ever released publicly. With the first couple of implementations were based on skinning from fuselage and stack, and it just didn't work well. It just wasn't intuitive. It was really difficult. And to the point that Nat made yesterday when she was talking about her engine modeling experience, that the hard part was figuring out how to make it intuitive and how to make it easy for the user. That was absolutely true with blended wing. I did multiple failed attempts before I finally got something I was happy enough with to release to people, and I've been really happy with how it was. So, transitioning from there, I'll start the next talk. This is something that we haven't done at past workshops, and so I apologize ahead of time if we lose some people, but at the same time, I hope we gain some people that's maybe just what they're looking for. This is going to be an under the hood tour of what's going on in the source code of VSP. It's a big code base. We're not going to have time for everything, but I hope to get you a guided tour that'll hopefully help you find your way if you ever come back. So I'm Rob McDonald, and we'll go from there. So first, Justin Gravitt did a great job last year of doing a follow-along tutorial of how to compile OpenVSP on Windows. And most of our users are Windows users, so we're not going to repeat that for Mac or for Linux. But if you want to see how to compile it, go to last year. He's got his video and his slides are a great step-by-step walkthrough of how to compile. He also talked about how to make contributions with Git, and we don't have time to really get into Git usage here today, so we're not gonna bounce on that too much. We're also not gonna get super in depth into CMake or Swig or some of the other tools that we use. What we are gonna try and do is just give everybody a guided tour through the source code, like I said, to hopefully find your way if you ever make a wrong turn and end up in the source code sometime in the future. So with that, sort of the top view of the source repository is a whole bunch of directories. And I've done this exploded tree view, and we're going to walk through a bunch of these in general. We have a directory that contains a bunch of external libraries, some examples, and then most of the source, which also has some code that we call external. It's not really developed by the core developers. And then over here on the right is sort of the things that really are developed by the core developers. So it can be daunting, but we're going to walk through a lot of this and hopefully help make some sense of what's going on here. For the record, the code that really is sort of core VSP, that sort of we own ourselves, is about 250,000 lines of code. So that's not small. It's a big package. I'm counting everything over here in this source directory, so none of the external contributions. Of that, about 45,000 lines of code is VSP Arrow and its solver and slicer and viewer. So if you took that out, maybe VSP itself is back down to about 200,000 lines of code. But there's an exception I'll talk about a little bit later. One of these libraries over here that's hidden away is really our own core source code called Code Eli. So we'll add that back in. But in any case, this is a big project, and hopefully this tour will help people find their way if they need to. First, let's talk a little bit about the tool chain, the things that you need in order to build and develop on VSP. Again, we're not walking through the process, but I wanted to just give some words to these, make sure everybody understands. We use CMake as a cross-platform build tool, and what that means is CMake is a meta build tool. We use it to build our build files. So if you've ever worked in Visual Studio, you know that you have visual project files. CMake makes those project files. Or if you've ever worked in a Unix type environment and you've used make files, CMake makes the make files. And it's really essential to us so that we can work in a cross-platform way. We can manage one set of CMake files, and that allows us to build on different platforms and different build systems. We use Git as a version control system, and we host on GitHub. And so that's where the source code is hosted and where we share and where we merge different contributions. And if you want to get the latest, greatest source code, that's where you go. You go to GitHub, you need to know how to use Git and pull that down. You're going to need a C++ compiler that supports C++11. Pretty much any compiler will support that these days. And we regularly compile with GCC, Microsoft, CLang, and Xcode. So I know that people in the past have built with Intel C++. I don't have access to it. I think it'll work fine, but I haven't tried it lately. And if you're going to build anything on VSP, you've got to have these three. There's some additional tools which are what I'll call optional. We use something called Swig, which is a wrapper interface generator. That's what takes our C++ API and turns it into something that Python and MATLAB can build against. And so if you want to develop and you are going to be developing to the API, to either Python or MATLAB or Java or something like that, you're going to need to install Swig on your computer as well. And if you're doing that, you also, of course, need the corresponding Python and MATLAB that you're going to work with. Another optional thing in the build toolchain is Doxygen. This is a documentation generator. This is how we generate the API documentation that's on the website. The only reason you need Doxygen is if you want to make your own documentation. So you don't really need to install it, but if you're making changes to the API and then you're making changes to the documentation, then, and you want to check to make sure that the documentation came out the way you wanted it, then you're going to want Doxygen installed, and you're going to be able to use that to process and generate the HTML documentation. Here's a little secret that most people don't know. If you're at the command line and you run VSP with a -doc, it'll actually run and generate these 3 files, which constitute the documentation, that what we use to process and create the documentation for the API. There's a little README. There's an actual script which will run the example code in every single API doc. So you notice every API documentation, every routine has a little example. That code gets pulled out and you can run it as a script. And then this OpenVSP AS.h, there's an underscore here that you can't see. This is actually what gets processed by Doxygen to turn into that documentation. So this header file, it's not really a header file, but it looks like one, and that's what all our documentation is generated from. There's a couple of different ways to build. I'll fly through this. But basically, CMake follows instructions, and those instructions are always found in a CMake list text file. And if you're doing a CMake project, you're going to find there's going to be one of these CMake list files in almost every directory. They're littered all over the place because one will call another and will call another. In OpenVSP, there's really 4 ways to start. You can think of this as 4 front doors to get into our build process. There's a CMake list in the external libraries, in the libraries directory, and that's only going to do the external libraries. We have a super project, which builds both the libraries and VSP in one go. There's the source, which builds VSP and VSP Arrow. And then we've got sort of this top level wrapper, which is really just a redirect to the source. And that's probably the one that I recommend a lot. If you're just porting VSP to a computer where you're not going to be hacking on the code, but you just need VSP to compile on some machine for some reason, then you might want to use the super project, because it should do it all in one step. You're not going to be getting too much under the hood, and it should be a pretty direct thing. Unfortunately, the developers hardly ever use it, so it doesn't get tested very often. So it occasionally breaks. And if it does fail, then use one of the other front doors. If you're a developer where you're going to be really getting into the code and rolling up your sleeves, then I recommend you build the libraries separately from the project. And that way, what that does is it means that every time you build a project, you don't have to go back and rebuild the libraries. You don't even have to check if they need to be rebuilt. It'll just assume that they haven't been changed, and you can just focus on the source. So it makes a more efficient process if you work with them separately. And then if you choose this top level entry point, it'll allow your IDE, like Visual Studio, to see all of the files. It'll let you see the libraries and the examples. It'll let you see. It really means that if you start at the top level, your IDE will see everything in this tree. Whereas if you start with pointing your IDE here at source, you'll only see everything from here down. And this stuff up here will be invisible to your IDE. And I like to be able to see the examples in my IDE. So I recommend you start with this top level redirect. Now that libraries directory has a bunch of external libraries. So when I was counting up that 250,000 lines of code earlier, that's not counting other people's code that we count on and we rely on to be correct that we didn't write. These are just other people's code that we're using. And we kind of have a different relationship with different projects. So there's a bunch of projects that we pretty much treat as a black box. We don't poke around in the source. We just take it as good. We don't modify it. We try to keep up to date when they release new versions, but we don't mess with them. We're not involved in their user communities, anything like that. And that includes things like, well, everything in this list here. We have something I'm going to call a gray box, which these are things where we might go in and make a change occasionally. We participate some in their user communities. We're a little bit more up to date and a little bit more involved, but we really still don't own these. And the 2 biggest examples of this are libIGES and stepcode. These are the libraries that allow us to write out IGES and step files. And it's been important for us to be involved because these are both really young projects that are really small, and we were some of the first users of them. And so when we started using them, they were broken, and we had to help them, find bugs and debug and get things working. So we've been involved in libIGES and stepcode. FLTK, is the library that we use to create our GUI. That's all the buttons and the windows and the scroll bars and things like that. And so we're pretty just intimately connected to that. And so we have to stay up to date with FLTK's changes. And again, we've occasionally found bugs that we've had to work with that community to fix. So we have a little bit more intimate relationship with these than we do the others. And then we've got two where I call them no box. And what that means is that these two are really, even though we've placed them in this external libraries directory, they're not external. These are really just a part of OpenVSP's code that we've just organized differently. One is the expression parser that makes Smart Update work. I don't know if we talked about Smart Update. It's just a little algebra parser that does addition, subtraction, multiplication, division, things like that. And then Code Eli, this is the big one. Our really low level, our Bezier curves and surfaces, our hardcore math, that's all done in Code Eli. So that's about 70,000 lines of code that we really own, even though it's located in here in these external libraries. Now we call them internal libraries, sort of. I'm saying it here. I'm saying it's internal because it's in the main build, not the library's build, but they're in the external directory. They're in source external. And we have, again, there's a bunch of these things that do different functions for us. We have a similar relationship. Some of them are that distant black box. We just take them as a given and we really don't touch their source or interact with them. We have some that are more gray box where we have, closer interaction. We've had to make changes. We interact and you may occasionally need to have deeper knowledge of these in order to work. And then we have some what we call no box, where these are really things that we own, we've just put there. So for example, the NACA 6 series airfoil generator is actually a C code that we've converted from the Fortran to do the math for 6 series airfoil. So that's an original NASA code for that. And then likewise, we have an Edmonton Lord, that Fourier series computation I was talking about yesterday. The code that does that is in this little area. But these are both pretty small, but we really own both of these. Nobody else, they're not an external project. They're just organized here. Of course, there's VSP Arrow, and that's in that source directory located in VSP_Arrow with Slicer Solver and Viewer as separate directories. And the VSP source code is completely separate of VSP. It's not sharing any files or linking across it. It's a separate thing. And we use CMake to build it, but Dave Kinney, he does it using handwritten make files, and he's building on Linux only. So that means the VSP team integrates that into our build system and makes it work with CMake and makes it work across platform. The viewer does use two of the libraries from the rest of the framework. It uses those STV libraries for writing PNG files for screenshots and animations. And it also uses FLTK. And so that's that GUI library for the buttons and the scroll bars. So it uses that. And when you're building it from CMake, it gets it from our project. If you're going to build it using Dave's make files, then you have to provide the STB image file and the FLTK stuff. You have to provide that yourself in order to make the make files work. It's a VSP Arrow. The solver itself is a little bit tricky, and that's because it uses OpenMP to get multi-threaded versions. And the problem with that is then there's certain extra libraries that need to be bundled or that need to exist in order for the OpenMP to then run on the ultimate user's computer. And Windows, there's a trick in CMake to help us grab those DLLs. And so you'll notice there's some weird named DLLs in the zip file that come along with VSP. Those are going to be the OpenMP DLLs on Windows. On Linux, the OpenMP libraries are usually installed. Everybody's computer's got them. It's fine. Or GCC has the ability to statically link those libraries, so we can tightly bundle it. On a Mac, it's a hassle because most of the time OpenMP libraries are not installed, and the CLang Xcode does not support static linking. So we've had to work around this in the past, where we'll actually use a second compiler. If you compile most of VSP with Clang or Xcode, then on a Mac, we're actually going to use GCC to compile VSP Arrow itself. And that's all about this OpenMP stuff. So you'll notice there's some complication if you dive in what's going on with CMake here and the compilers around VSP Arrow. Okay, if you're working in the API bindings, there's these two directories for the MATLAB API and the Python API, and these include some files that go to Swig. And so if Swig is installed, then you can build these things. It'll then also look for the Python or MATLAB to do it. And the bindings are based on the API on the C++ side. And then we also have the AngelScript version. So these two need to match, and that's a little bit of a manual process. So it's possible for us to leave some things out that we put into the AngelScript API, but we forget to add to the C++ API. So we need to watch for that. But detailed instructions on how to do this were given by Justin back in those slides. And the result of this binding is either a DLL or a shared object file that basically puts all of VSP into a file that then the scripting language can call. You need to be a little careful because these need to match. If you're using, 64-bit Python but 32-bit VSP, it's not going to work. So you need to match, if it's Python 3 versus another one's Python 2, they're not going to work. So you have to match it up, and we try and do that. We're currently bundling Python 3.6 on Windows and Mac, and then on Ubuntu, we use whatever the Python that system installed is, and that's what we try and target. Hopefully that works for most people, but 3.6 is getting a little bit long in the tooth. So, comment in the questions if you think we should update to a newer Python. Okay, now we're finally getting to VSP itself, right? That's just been some of the ancillaries and around the edges. So the main part of the VSP code kind of comes into these directories here. And I'm going to start, we're in version 3 now, but first I'm going to talk a little bit about version 2 and before, sort of the ancient history. In the ancient history of VSP, in this box in the upper right, if you think about 3 main functions of VSP, 3 roles that needed to be done, there's sort of the geometry math itself, the thing that actually figures out, given parameters, where is the wing surface, where is the pod surface. So that's the geometry. There's the GUI, that's the buttons and the sliders, and making it interactive for the user. And then we've got the 3D graphics, everything that goes into that big window where we show you the model, where we show you the airplane. And what I'm trying to represent with this Venn diagram up here is in V2, this code was inseparable. It was all together in the same source code, sometimes in the same functions. You'd have one update routine, and it would come, and at the start, it would update, and it would do some of the math for the geometry, and then it would update the buttons in the GUI for the geom window, and then it would update the 3D graphics. And so this code was all together as a big mashup. And when we did the rewrite to go from V2 to V3, one of the big goals was to break this apart, was to separate these. And the reason is that if you're working on a high performance computer, like a supercomputer, there's oftentimes you don't have the ability to have graphics libraries. Things like OpenGL will not be allowed to be installed on that computer. And other libraries that go with that won't be able to go along. And so we had to separate this. And so version 3, we had to separate the geometry from the GUI and the graphics. And I've drawn this broken yellow line here with the gray behind it. Think of this like a road. And what this means is that if you're on the side of the road with the GUI and the graphics, you can cross over to the other side. You can see what's going on in the geometry. You can access these things. But on the other hand, if you're over here on the geometry side, you can't see. This is an impenetrable wall. You can't communicate to the graphics and the GUI. And this is very important architecturally. And this includes any source files or any headers. If you're working on something that's in the geometry core, you cannot include any source files or any headers or use any functions or methods from the graphics or from the GUI. These things do not exist to you. You only exist over here. Whereas if you're in the GUI or in the graphics and you need something from geometry, you can just kind of reach across and take it. So there's this asymmetry in the design that's important, and it goes all the way through to things like header visibility, function visibility, and where we go from there. These colors up here in this top represent the main directories. So anything that's this light blue, which is util, geom core, and CFD mesh, these 3 really exist on the geometry side. They can't see 3D graphics or GUI. but they can be seen by them. Oh, and XML VSP. Whereas this hot pink GUI and draw is the GUI code, and this, I don't know, tan, whatever it is, VSP graphic is the 3D graphics code. So those can see across that way. The things I've left out is the Geom API and the VSP directories themselves. They're actually both kind of small. And what VSP really does is all it provides is the main entry point. So you know, any C or C++ program, if you've ever done any of that kind of programming, every program must have a main method or a main function. And so that's pretty much all that's in this VSP directory, is the different mains. And we have different ones in VSP. We've got the main VSP executable that everybody runs, but some people, and so its main exists in that directory, but it has to obviously have access to the graphics and the GUI because you've used those. But then there's also VSP batch, and that is sort of the script only version of VSP. And its main file still exists in this directory, but it does not have access to the graphics and the GUI. And if you look at it, VSP batch can be run on a high performance computer with no graphics support. And then we've got some API things that go with this, and some tests that, again, these mains are separated up. And the API has to cross this line. So anything in white, there's some dancing around in those files as to whether they allow you to access the GUI or not. Whereas anything in the blue, you just can't access it at all. And then in the pink and the graphics, you can. So that's sort of an overall design that's fundamental to things that show up. We have some things that I'll call built-in libraries. I know I'm abusing these terms a little bit, but basically util and XML VSP are a collection of utilities and things that we use in-house, and they're pretty much just set up like a little library. XML VSP is just a small number of simple wrappers that make it easier for us to use libxml2. VSP doesn't really have an XML schema or an XML file format in the traditional sense. There's no document where you can go and I can tell somebody else, here's how to read a VSP file. And that's kind of a broken concept, the way VSP is designed, in that the file is incredibly dynamic. Things can be added or removed from the file all the time. Things like those custom components, that engine that Nat showed yesterday, I have no idea what parameters she built into her model, but that model has to be able to be represented in the file. So the file itself is dynamic. So when you're working with VSP, don't read and write the XML file directly. There's some legacy applications where people have done this. They think they're very clever, but it's really a terrible idea. It's not meant for that. Strongly discouraged. Don't read and write the XML file. If you want to interact with VSP closely, use the API, communicate that way. You're going to be a lot happier with yourself. There's also the util directory, and that has a whole bunch of small classes. The most commonly used things are our point or vector class, vec3d and vec2d, a transformation matrix class, our sort of underlying curve classes, VSP curve and VSP surf. There's a message manager. I'm not going to have time to get into that. And then something that is what moves the draw objects, the 3D graphics information around. There's a lot more. There's actually about 30, maybe more than that, things in util, but these are the most commonly used. You're going to see a whole bunch of things that we call managers across the OpenVSP source. Here I'm just using generically, I'm calling it foo manager. That's not real, but we use managers a lot. And if you're familiar with C++ programming or object-oriented programming, they're really what we call a singleton. It's a design pattern, and it kind of works like a big global variable. And each manager is a place where you can put a bunch of data that then is going to be accessible from anywhere, almost anywhere in VSP. So things like the vehicle model itself, or accessing all the parameters, or advanced links, a lot of these things have their own manager. And there's a bunch of them. And they follow this kind of a pattern where, again, this is something only C++ people could love, but it just sets up a singleton. You'll access it through this define down here, where foo manager then returns manager singleton get instance, which calls here, we've got a static singleton instance, so there will only ever be one of them, and we return a reference to that. So it acts like a pointer You treat this like a pointer. You use a dash and an arrow after it to dereference from it. You can't, the constructors don't work, the destructors don't work, but they're going to be available everywhere. And you don't have to create them anywhere. The first time somebody uses them, they'll get created on the fly. So we use a lot of managers, and if you see something that's a manager, that's what's going on with it. The directory GUI and draw, this is really what handles all the buttons and sliders and pull down menus and things like that in OpenVSP. And if you're familiar with GUI design theory, there's something called Model View Container. Model View Controller. MVC is a standard design program in how GUIs are done in an event-driven, object-oriented environment. And we do that too. And I would say that GUI and draw is where the view and controller part of model view controller happens, where the model is over in Geom Core. And again, the model is often done via singletons, so that they're always available from every place. There's going to be a lot of update methods, and the view in particular goes through and updates the view. And what you want to think about here, what I'm trying to express, is you may think that the best way, if somebody goes in and they move one slider and they adjust one parameter, you may think the best thing to do is to go back and as that slider is moved, to update just the value that goes with that one slider. You know, if they drag a slider from aspect ratio and it was 4 and they drag it to 6, you may think, oh, I only want to go through and update the box that says 6. And that would be a very fine-grained update. But what it would mean is you would need custom special code for every single box, for every single parm in how to update it. And so we don't do that. Instead, when you update a view, it's essentially more of a slash and burn. And what that means is every time a GUI update gets called, that means we update the entire GUI. We start at the beginning and we go all the way through, and every single field is updated every single time. And there's actually an update loop in VSP that could be happening 30 times a second. So it happens real fast, but we don't do a fine-grained update. We don't try and get too cute. We just go through and update the whole thing. The GUI itself, the layout of the buttons, the sliders, the windows, that's done in code. So if you're at all familiar with GUI design, you'll know that there's sort of 2 ways to do it. You can either write code that says, you know, I want a button here, I want it this wide, I want it this XY. Or there's sort of drawing programs where you can go in and you can drag and drop and change the size and arrange a GUI in a graphical, what you see is what you get, drawing program. FLTK supports that. FLTK's drawing program for that is called Fluid, and it creates something called .fl files. And that's how Kenny does it over for the VSP viewer. He uses Fluid with FL files to draw that GUI, and then you run Fluid and it actually generates C++ source code that then gets compiled and becomes that GUI. On the VSP side of things, we don't use Fluid. We used to in version 2, but in version 3, and it took a long time to get rid of the last uses of Fluid, but we actually we make all of our GUIs programmatically. And so every button is added with an add button command. And this has really made it a lot easier to maintain and for consistency as things go forward. So all this stuff is in GUI and draw. The main classes you need to know about in GUI and draw is we have this GUI device class, and that's all of our buttons and sliders and pull downs. These are all of the widgets from FLTK, but they've been enhanced to sort of know about OpenVSP's framework and how parameters work and how things work in OpenVSP. So the GUI devices are our widgets. Group layout is the class that we use to lay them out into a GUI. So the thing that's going to position and help size our buttons, that's all done there in group layout. Screen base is our basic screen class. If you're making a screen, you're going to inherit from that and build from there. And geom screen is implemented in there as well. So the main geom screen that has things like the general tab and the XForm tab and the subsurface tab, all of that's implemented in geom screen and screen base. Screen manager is the owner, right? It owns all the screens in VSP. So that's where they're all called from, and that's where updates originate from. when screens need updating, we tell Screen Manager to update screens, and it goes through and it looks which screens are currently visible, and it tells all of them to update. Main VSP screen is the big window on the left that has the pull down menus for file and view and window and analysis and things like that. So that's where all of those pull down menus are set up. Manage geom screen is the one that is always open when you open, that's paired with it when you start VSP. And that's the one that has the tree viewer in there that you can select which geom you're using, show, no show, hide, shade, all those things are in the manage geom screen. The main GL window is sort of the 3D graphics portal that gets placed inside the main VSP screen. So if you're looking at anything 3D graphics, you can kind of start there for where to look. And then in this directory, there's a whole lot of screen files. I call them foo screen because there's going to be wing screen, pod screen, geom screen, VSP arrow screen, projected area screen, right? Everything's got a screen. There's going to be many of them, and each one is the implementation of the screen for that particular feature. The 3D graphics is OpenGL stuff, and that's all pretty much located in the VSP graphic directory. And this provides the interface between our code and your graphics card hardware, and that's done via OpenGL. The bad news is that OpenGL is being deprecated by pretty much everybody. It's being replaced by Direct3D on Windows, Metal on Mac, and Vulkan everywhere else. And that's a challenge, because if people really go through with deprecating this, then VSP is going to need a major rewrite of the graphics subsystem in order to keep working. And that terrifies me. That's going to be big and scary. Right now, OpenGL is still working, but we need to worry about that down the road. The way this communication works, there's sort of a handful of things. And this is in the geom core side of things, there's a bunch of methods you'll see called update draw obj. And what those do is they get called by the geom's own update. This is what sort of does the math to set up the mesh that gets visualized. And this is what positions those points that OpenGL is going to look at. And when these are changed, it's going to set a flag, mgeom changed, it's going to set that flag to true. Now, VSP GL window, we just talked about it. When its update gets called, it's going to call load draw obj across a bunch of places. And that load draw obj is going to update the GL window. It's going to load all that data and transfer it over to the video card. And once it's done, it's going to set that geom change to false. And so, if it ever notices that the geom has not been changed, then it's not going to transfer the data. So this is an optimization that means that if we haven't changed the wing, we don't transfer the wing every time. Load draw obj gets implemented all over the place. And what it does is it transfers the draw obj that was created by the update draw obj. And it's the collector. It's like a garbage man going along and picking up draw obj at every address in your street. Load draw obj can make small adjustments. You can't change the bulk shape, but for example, you can change if it was shaded versus wireframe, or change the color. You can do that in load draw obj, and it'll be faster if you do it there than doing a full update draw obj with the geom change true. VSP GL window, the underscore update, which gets called by the main update, that's what actually goes through and creates entities on the OpenGL side that correspond to every draw object. So this is really what transfers things to the memory of the video card. Every draw object that we have, it says it has a geom ID. It's not really a geom ID, but it is a unique identifier. It's a unique identifier. And the reason we do that is when we transfer some draw object to the video card, we need a way coming back later to see if it's the same draw object. So we give it this unique ID, and that allows us to come back and check to see if it's been updated or not. So that ID needs to be unique, and we're going to use that in conjunction with the geom change true false flags. And then that geom change flag is really the flag that tells us to trigger the bulk updated data. So that's how that'll trigger. And this is kind of how how we communicate from the core subsystems over to the graphics card. Most of these classes, you're going to find draw obj as in util, and that's just this little transport carrier. In VSP graphic entities, that's what actually goes through and does the drawing. And scene is what does the drawings in the scene. So the low-level drawing is drawn by entity, and scene handles drawing everything as a whole. So that's sort of the top level where to go look for where stuff is happening there. Okay, there's the CFD mesh directory. And while it's called CFD mesh, that's kind of historical reasons. It's where we have all the code for the CFD mesh, FEA mesh, and the trim surfaces for the trim surfaces output to CAD that Justin talked about the other day. And there's sort of two main algorithms that happen in here. One is the surface-surface intersection of the smooth Bezier surfaces. And then we also have our isotropic surface mesh generator. And those are sort of two core algorithms, two really hard things to do that exist in this directory. And then we use them in different ways in order to make the CFD mesh, FEA mesh, and trim surfaces utilities that the user can use. Historically, go back a long time, all these files were a part of Geom Core. We haven't talked about that yet, but it's up soon. But we separated them out to declutter things. So now they're in their own directory. But we need more of that. We need more of this kind of separation. And really, it'd be a great idea to turn CFD mesh into a standalone library so that it could be called separately and it could have its own main and its own tests to really help us improve our unit testing and improve its reliability. So that's something that needs to happen as we mature. It's going to take a bunch of work, so I'm not sure where the time and the resources will come for that, but keep your eye out that these things need to be refactored and separated out. Okay. Geom Core is everything else, right? You may be wondering where's all the big stuff? Well, it's kind of all dumped here in Geom Core. And like I said with CFD mesh, it would be great to separate a bunch of this into other subdirectories to clean it up, separate it off, and where possible, refactor some of it into libraries with their own APIs and the ability to make their own tests to improve the quality of that code. I'm going to break this into, there's sort of 5 groups of classes and functions in here. There's things that I would call sort of boilerplate infrastructure. There's the scaffolding that makes it all work. There's the geometry itself. There's things that kind of relate to the modeling tab in the menu for manipulating a model and making models smart. There's things that relate to the analysis pull down in the menu that allow us to do different algorithms and analysis on things. And then there's kind of some other stuff that doesn't fit this taxonomy, just everything else that we can toss in, like lighting and measures and textures and custom geoms and other stuff. So we're going to talk through some of this here, not in tremendous detail, but hopefully it'll give a flavor of what all's in there. In terms of infrastructure, what you need to know, there's something called a parm, and that's a class. You'll find the parm files in there. And that represents the parameter that we vary itself. So every parameter in VSP, whether it's sweep, taper, exposition, twist, fineness ratio, skinning variables, all those things are parms. Every slider you move, you're adjusting a parm. And the parm has to know its lower limit, its upper unit limit, its name, its group, its value. All these things are known by a parm. They also have unique IDs, and that unique ID is what allows us to do things like fit model and design variables and other things, because we don't always have to keep track of a parm by its full address. We can just talk about it by using its unique ID, and that's really powerful. More of the infrastructure is something we call a parm container, and a parm container is something that has a bunch of parms. So the vehicle model itself, geoms are parm containers. Sometimes different managers for the VSP Arrow GUI, there'll be a parm container there. So it's a thing that has a bunch of parms. It also has a unique ID. So each geom has a unique ID, and we use that a lot. Parm manager, right? This is what keeps track of all the parms. All the parms ultimately are tracked by the parm manager. And if you want a parm and you know its ID, you can ask parm manager for it, and it'll send you back a pointer to that parm. Vehicle is sort of the overall model. It is a parm container. It's accessible through a singleton. You can only have one vehicle at a time, and that's what keeps any data that that belongs to the model but that doesn't belong to a geom ends up in vehicle. Now, when a parm is changed, when you change the value, it doesn't call update immediately. Instead, it's going to call the parm container that it's in. It's going to call that parm container's parm changed. And so we're now notifying its parm that it was changed. So you can imagine this means that if you change sweep angle, then it's going to notify the wing so that it knows, hey, wing, your sweep angle changed. And it's then going to set a flag that we call this late update flag. And maybe we should change the name of this to needs update flag. What we mean here is we've quote unquote dirtied the geometry. We've said, look, it's no longer up to date. It needs to be updated later in order to be up to date. So we set that late update flag to true. And then later down through something else in the code, an update cycle is going to happen, and it's going to go through looking through the model, looking for things that need to be updated. It's going to do that update, and when it does so, it's going to set late update flag back to false so that we know we're current. And this is really important. You can imagine when you load a VSP3 file at the beginning, there's thousands of parms in that file. And if after every parm was updated, every parm was set as we read in the file, if we issued an update, that would mean that reading a file in for the first time would trigger thousands of updates, and it would take forever long. So instead, what we can do is we can sort of batch these updates together. Every parm that's read in from the file, it sets late update flag to true, but we don't trigger an update until we're done reading in the file. And then once we're done, we say, let it rip, fire off all the updates, and it goes through and everything gets updated. So that's what's going on there to keep things efficient. Okay.
Hey, Rob, real quick, while we're on the subject of Parm Manager and Container, Jason's asking how Parm Container and Parm Manager differ from each other.
So there can be lots of parm containers. The vehicle is a parm container. Every geom is a parm container. If a geom is something made up of multiple execs, then there's going to be an exec surf in there that's a parm container. And each exec is a parm container, and each exec has an exec curve, and each exec curve is a parm container. So a parm container is just something that has its own little parms, whereas parm manager it doesn't actually have any parms itself. It's sort of like the watcher, right? It keeps track of all the parms. It knows where they all are. It knows all their pointers, but it doesn't have any of its own. So back in the old days, long ago, analysis tools were added to VSP in an ad hoc basis. Every time we'd add an analysis tool, whether it was CompGeom or area slice, things like that, each one, we would just go into the API and we'd like, oh, we need CompGeom in the API. Let's go add, run CompGeom to the API. Let's go add run slice to the API. And each one has its own parameters and has its own output. And this was all done in an ad hoc way that each one made sense for its own function. It made sense for CompGeom, for area slice, or for whatever what it was. But there was no commonality. There wasn't a standard way of doing this. And as we grew and as we added a bunch of analysis types, it became clear that we needed a unified approach. We needed one way to talk to all these analyses. And what we did was we came up with sort of a couple of layers. First off, we're going to talk to these analyses through a name value pair system. So any input value, say we're sending VSP arrow the Mach number, we're going to have a list of inputs, VSP arrow inputs, and we could say VSP arrow, hey, what are your inputs? And it's going to come back and it's going to give us a list of names. One of them will be Mach. And it's got a name that we can interact with, we can search, we can read, and then a value that we can set. So we can tell, VSP arrow, we can say, hey, what's your Mach number? Set the value to 0.6. And so this name value data and name value collection are the two classes that work with this. And these are the low-level classes that let us work with this kind of information. And if you're a Python person, you might call this a dictionary, where a name value collection is really the dictionary, and a name value data is a single element in a dictionary. Now then what we do is the outputs, when we take all the outputs from an analysis, we put them all into a results class, and that results class is a name value collection. But then there's a master results manager that holds them all. So there's the results manager class. When you run an analysis, it creates a results, it throws it over there in the results manager class, and it dumps that out. And so through the API, you can access any results from any analysis that's run through the results manager. And then likewise, there's an analysis manager that manages all the analysis tools. And to add a new analysis to VSP, you really only have to implement two methods, which is basically something that sets the default values and something that tells it to run. And of course, when it runs and executes, it returns back an ID to a unique results object. So if you're working on adding an analysis to VSP, these are the things you need to look at. You need to go to the analysis manager. You need to tell the analysis manager that your new analysis exists. So you have to register the built-ins, and then you write that execute so that it'll create results. And then everything should be hooked up for that to work. Okay, I realize I've gone long, but I hope everybody's finding this useful. I'm going to keep going, power through. Now we're getting into the nitty gritty, if you think that's possible. So at the core of everything, where sort of the real magic happens, where the math happens, that turns a set of parameter values into a shape that a user sees, that really happens in the update method of geom. So if you're going to write your own geom, and if you want to change a geom, change its behavior, you're going to need to come in and you're going to need to make changes to geom update. And so first we'll talk a little bit about the classes. A geom itself is derived from, it is a geomx form, which is derived from a geom base, which is derived from a parm container. So to Jason's question, a parm container is a base class that a geom is derived from. And we've implemented some of the base and transformation functions of a geom in these levels, and then everything else is here in geom. And so that's sort of the main geometry class, base class, that if you're implementing your own geometry, you'll probably start from. And then it's got this method update, which handles most of the work. That's where most of the heavy lifting of being a geom is done. And this was recently changed in 3.22. I made some major changes to geom update to make it smarter about the work. And you know, I talked about doing a fine-grained or a coarse-grained update earlier with respect to the GUI. Essentially what we did here was I went through and I tried to make geom update more fine-grained. And what this does is it made it a lot faster, and I've been calling these the new faster update changes, but it had a lot of risk, and frankly, it introduced a bunch of bugs. I think we've finally got most of them chased out, but that's the trade-off, right? Is we've added more code complexity, and with that came bugs, but the code complexity was able to, frankly, we also need more memory. We use more memory, but we then also get higher performance. So that was all done. If you go into geom update, you're going to see there's a geom base method, and it is called set dirty flags. And what we do, rather than go to perfectly fine-grained, right? You can imagine a fine-grained update would know what is the minimum things that need to be done if I change one parameter, right? If one parameter changes, what needs to be updated? What's the minimum things to still get a consistent answer? And figuring that out on a individual parameter by parameter basis, parm by parm, would be incredibly challenging, and we're not equipped for that. We didn't design VSP for that. So instead, what I did when I made faster update, my observation was that I could kind of group update changes. I could group them. And so there's certain parms that affect the position, rotation, and symmetry of a geom but without changing its actual shape. And there's other parms that affect the tessellation, the wireframe tessellation, and the clustering of the representation on screen, but they don't affect anything else. They don't affect its position, orientation, or symmetry, and they don't affect the underlying shape. And then there's other parms that affect the shape itself, that affect the wingspan, the airfoil shape, and basically anything else, right? It's a catch-all. Anything else goes into that. And so what we can do is when parm changed is run, parm changed for a geom will call geom-based set dirty flags. And set dirty flags is like the triage nurse. It looks at each parm and it figures out, and this is basically manual code, it figures out, is this parm that changed, is it an X form dirty? Should it mark that as changing the transformations? Should it mark it as changing the tessellation? Or should it mark it as changing the surface itself? So this is the triage to classify any parm. And that'll go through and propagate that information. And just ignore this little bit down here. Well, I guess I'll talk about it. There's something in update called, I think it's on the next slide, update surf. Yeah, I'll assume it's on the next slide. We'll come back if we don't. So that's what's going on in geom update with faster update is we have to triage these every parm so that then update can only update the things that need to be updated. Update surf is where the particular math for your given component, for your given geom is implemented. So much of what happens for a geom, you can imagine things like positioning it 3D space and handling symmetry and its color, all of these things, those are all the same, right? They're all generic for any geom, and you don't need to implement that code over and over again. So that's all updated, that's all handled in geom update. But an individual, a particular geom, whether it's a wing or a stack or a body of revolution, any foo geom needs to update its surface. And this is where the particular math that's particular to a propeller or to a pod or to a fuselage, that's where it is implemented. So that's sort of the real core to a surface is how do you turn parms into a surface is for a geom is here in update surf. And what its job is it populates this main surf vec. Okay. Its job is to do the math and populate main surf vec. And main surf vec contains a single copy of the geometry with no symmetry applied and no transformation. So it's at the origin, aligned with the axes, a single copy of all the surfaces of a geometry. And all the built-in surfaces really only have one surf, right? There's only one surf for a wing. But some of the custom geoms, if you think about something like Podman and seat, there's the back of the seat and then there's the butt of the seat. So there's actually two main surfaces in this surface vec. But there's only one copy of it, right? It has not been transformed or positioned in space. But that's really what update surf does, is it lofts the surface and puts that there. And under the hood, main surf vec is an STL vector of VSP surfs. VSP surf exists in util. We talked about that earlier. Under the hood of VSP surf, the actual math is VSP surf has a member variable called mSurface, which is a piecewise surface type. For those of you that love templated code, a piecewise surface type is a type def. Here you can see piecewise surface type. It's really from Code Eli. Remember I said that there's that math and surface library that's where all the low-level stuff happens. So that's Code Eli, and it's a namespace haven. So in an Eli geom surface piecewise, which is templated to use Eli geom surface Bezier surface patches based on double variables in 3 dimensions, because we exist in 3 dimensions, is a piecewise surface type. So the low-level math is really handled by this piecewise surface type, which again is a member of a VSP surf, which then there's a vector of those that are the main surface vec. And then we've got this method called apply symmetry, apply sim, that takes a vector, which is the main surface vec, and it applies the symmetry and transformation things to make all of the copies. So it copies main surface vec to create surface vec. So that's where it goes through to make all of those symmetrical copies, as we apply sim to main surface vec to then go to surface vec. And we actually use apply sim a couple of other places as well. Okay.
We've had a question pop up here in the chat regarding the triage system of whether it spawns separate threads for the jobs and if they run parallel, or if this is more of a different implementation.
No, this is all single threaded. This whole bit, the only places where VSP itself uses threads is we'll spawn a thread for some of our analyses. So when we run VSP Arrow, we'll spawn a thread for that. We'll actually spawn a thread for CFD mesh and for FEA mesh, so that those things can kind of go off and run on their own. But the core of VSP itself is all single threaded. So that's yeah, I can't imagine trying to make all this thread safe. It was not designed that way from the start. So I don't know how we'd have to do that. Okay, good question though. Okay, if you find yourself in the position where you want to add a geom, you want to add something to VSP, you want to add your own geom, the places you're going to be working is in Geom Core and in GUI and Draw. And you need to know about the geom that's the main base class. But so to implement foo-geom, your favorite thing, you need to inherit classes, both one from geom and one from geom screen. So you're gonna make foo-geom and you're gonna inherit from geom, and you're gonna make foo screen, inherit from geom screen. And then you need to implement these methods. And there's only, what is this, 9 of them? This is really, this is basically it. This is all you really have to do to add a geom. You have to make a constructor, and the constructor is where you tell it what params there are. You know, if you're adding a new, you know, satellite dish component and you want it to have a diameter and a height, that's where you tell satellite dish geom that the params it has are diameter and height. You have to write update surf, and that's what takes the math for diameter and height and it makes it into a M surface vec. There's a compute center, which is really trivial. These are only like 3 lines long typically, but you notice there's an ability to change the center of rotation on most geoms. And so this is just where you're telling it, you just come back with an XYZ of where is that center of rotation relative to the body. And so that's what compute center does. There's a scale method. So I've talked about how the best way to design a component is with one dimensional variable, one thing that sets the scale, and all the other parameters, as much as possible, are all non-dimensional and scaled from that. What the scale method does is it comes in, and if it makes your object, it has to know which things are scale and which things are non-dimensional, and it's going to ignore the non-dimensional. But any of your params set up in the constructor, scale is going to go through, and if it's a dimensional thing, then it's going to, and you tell it to scale by 2, then it multiplies it by 2. So this is where the smarts to know that we scale lengths, but we don't scale angles, and we don't scale ratios. So lengths get scaled right here. Add default sources. CFD mesh has a button that any geom can have default sources added. This is optional. You don't have to implement it, but if you want default sources, this is where you come and you can make that happen. Somewhat similarly, if you want your geom to work well with conformal geometry, then this is where you come and you tell conformal geometry how to offset your surface and how to reloft it. So when conformal geom works, it kind of makes an underhanded copy of the geom. Let's say it's a wing. We make an underhanded copy of the wing, and then we go through and we do the math to say, okay, at each cross section, how would you shrink that cross section to make it conformal? And that math is done in offset cross sections. And when Brandon says that a propeller's conformal geom doesn't work very well, that's because I was lazy and I didn't do a good job of writing offset XX propeller, because I didn't think anybody would be crazy enough to offset a propeller. Brandon, of course, was, so maybe that needs to be done better. But I didn't think about using a propeller as a cutting surface the way he does. I was thinking that nobody would put a fuel tank inside a propeller. So, you have to worry about your assumptions about your users.
Yeah,
Once
sounds
you've
like
done
a
all
job
that,
for
that's pretty
future
much what you have to
Brandon.
do. On the geom side, on the screen side, you have to set up a constructor. So the constructor is what goes through the GUI devices and that layout that I talked about, and it's what adds all the buttons and the labels and sets it up to make your GUI look pretty. So you have to add a constructor, and then you add an update method, and that's just what goes through. And you can really think of the update method as being the pairing between this button that you added that you put the label sweep next to and the sweep parameter. You have to associate all the parms with the buttons. And so that's what the update does. There's a bunch of boilerplate. There's some plumbing and some connections that you have to make that are scattered around that you have to do to make all this work. But in terms of real work to actually implement a geom, this is it. This is all you have to do. Um, when you do this, you should do what I basically always do. And I start, if I'm adding a geom, I copy and paste pod geom. And I copy it, and then I go through and I change all the names so that instead of pod geom, it's now foo geom. And I make it foo screen. And I get everything working. I go through and I make everything work. I change everything from pod to foo. And when I'm done with that and it compiles and runs and I can do that, I usually make a git commit. And now I know that all my boilerplate is in place, right? I've got all that done. I don't have to worry about it anymore. And now I can just focus on these sort of 8 methods that are the real crux of what you're trying to accomplish. Likewise, if you want to do this, go study PodGeom. You'll see that everything I'm talking about here is on the order of maybe 100 lines of code. It's really quite simple. All right, we're getting to the end. There are some geoms that are more complicated than that. So, some geoms like pod are sort of standalone shapes. They do their own thing. Whereas some geoms like wing, stack, and fuselage, you notice that we have this collection and prop. We have this collection of cross sections. And so VSP has a class called geomexsec, which inherits from geom. And what geomexsec does is it then has an execsurf that then is a container for execs. And what execsurf lets you do is the boilerplate code to allow you to cut, copy, paste, delete, and work with execs in a generic way. And then an execsurf is itself a parm container, but it has an execsurf is a container. It has a bunch of execs, where each of those execs is what handles the positioning, the rotating and translating of a cross section for that. So there's a different way of doing that for a fuselage, a stack, a wing, and a prop, right? Each one of these contains its own sort of exec class that is the specialization, and that's what allows a wing to position the next exec based on taper, sweep, aspect ratio, span, whereas a stack positions the next one just based on XYZ, rotation XYZ. And that's handled by the exec. Then the curve shape itself, the exec class, again, handles the positioning of it. It also has an exec curve class. And so that exec curve is kind of like a 2D version of a geom. That's what knows about the 2D shape, whether it's a rounded rectangle or a circle or a NACA 4-digit airfoil. Exec curve is what does that 2D version of a shape. It's also a parm container. So, that NACA airfoil knows about thickness and camber, and it then creates its update function, basically turns the parm values into a VSP curve. So that's how these are added. And then exec curve is sort of generic, and we do points, ellipses, and rounded rectangles, whereas there's actually airfoils, which are a specialization of that. And that's specialized because it knows about chord and thickness to chord instead of width and height. And so all of our airfoil types are implemented as airfoil classes. Oops. And I know that this has been a fire hose, but hopefully that's a tour through OpenVSP. I'm happy to answer any more questions. And if anybody's really for it, I could go and show some source if anybody wanted to look at pod and how that works or something like that. But I'll take any questions now.
All right. Well, lots of information. Appreciate you walking through, and I mean, I learned a lot from that and taking a look at how to build geometries and things. And the nice thing is that the virtual workshop here has us recording all of this stuff, so I won't forget it in 2 months after I get caught up with other things. I can always go back and look at this and see it again. So I appreciate you taking the time to go with that. I don't see any Q&A on the IO page, and it looks like we've answered all the questions from the live chat over here.
Okay, I guess then just the last thing I'll say is if you want, first I want to encourage people. It's big, it's 300,000 lines of code, but I want to encourage people. It's not that bad. Things are pretty well defined and separated. It's not that bad to dive in. It's way easier today to make changes than it was back in version 2, even though the code is much bigger and much more complicated today. So don't be afraid of it. I see a lot of grad students in particular, but I see other researchers who are trying to accomplish things in VSP that would be a lot easier if they just open the hood and make a few changes. They're trying to fight the system or work around problems or make it do something that the developers never anticipated. And in a lot of cases it'd be a lot easier to just make it happen. So I encourage the grad students out there that are doing their thesis and trying to use VSP. Don't be totally intimidated. Open the hood, make it yours, make some modifications, see what you can do. The other thing I'll say is, if you know what you want to do, if you know what kind of modification you want to do, post a message on the Google group and ask where to start. This presentation hopefully will provide a top level view, but usually if somebody comes to me and says, hey, I want to do X, Y, Z, then I'm going to be able to come in and I'm going to be able to tell them, okay, you want to look at this class and this file, maybe you want to update this subroutine. So I can probably point you where you want to go and where you want to get started. And in my experience, when somebody's getting started in VSP, that's the hardest part, is figuring out where to start. And frankly, I'd estimate I've taught a number of people. I've brought them up to speed and got them current and good at developing in VSP. And I'd say that simply asking me where to start on a typical project will probably save you the first 2 weeks. That if you don't have this tour and if you don't know where to start, it'll take you 2 weeks to sort of figure out where you should do things. And I can probably tell you that in about 5 minutes. So don't be afraid to ask. I'm happy to help people get them started and save you that 2 weeks and get you started off to a good start from the beginning.
All right, thanks, Rob. Well, we've got our presentation here, and that concludes everything that was scheduled. We've got a little bit of time, and I don't know what everybody else has scheduled for the rest of the day today. But I know that there are some demo requests and some things that were asked for earlier the week, and I said that I'd get to it. So I'd like to take at least a little bit of time to try and show what was going on there. And there are some other tutorial requests as well. So there's some requests for like an advanced link demonstration and how to run VSP Arrow from the command line and stuff like that. So running VSP Arrow from the command line is a relatively simple demonstration. So I've actually been playing around with it a little bit here for the purpose of putting together a different demonstration. So running VSP Arrow from the command line is just a matter of pulling open a console window, and if you happen to do a change directory over to where OpenVSP is installed, is where it's located, you can just run VSP Arrow using VSP Arrow space filename _ digengeom enter. if you want to do a VLM mode. Now that's all predicated on the fact that you have already made your degenerate geometry, you have your VSPRO input files, but they're pretty easy to figure out what's going on. So I've got my notepad editor here, and these are some more, advanced VSPRO input files. But the stuff that you really will focus on are things like your reference area. All of this stuff is automatically generated by the GUI depending on whether you're running steady or unsteady and the type of run. So if you want an easy way to get started, run it from the GUI once, let it build all these things for you. Then go in and start tweaking things in an editor, save the file, and then you can run from command line. And that'll save you a whole bunch of headaches. So for the example here, if you want to run from somewhere not the OpenVSP directory, you give it, in quotes, you use the path, so C blah, 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 all the way out to where VSPRO exe is, put a quote around that, give it whatever options you want. In this case, I'm running OMP with 8 processors, and I'm telling it an unsteady run in this case, and then I tell it where my file is. So again, C blah, 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 drop pod degenerate geometry, and then that will execute VSPRO from the command line. So it's pretty easy to call. You can do the same thing with, say, VSP Viewer. If I were to go up and change VSPRO to VSP Viewer, get rid of this and tell it to call this, it will bring up the OpenVS or the VSPRO Viewer for me. So that's kind of a crash course into how you can execute VSPRO from the command line. There are a lot more options available than might be inherent to the GUI. And what should happen here is if I get rid of all the options and just tell run VSPRO exe, it will give you some extra information here. So it tells you that you can run in processes. It'll give you the option to do your stability derivatives. In that case, that is your 7 iterations on things like alpha, beta, Mach number, any control surface deflections and things like that you have in there. That's what the stab is for. And then you can override free stream values and paste that in. You can set up restart cases. You can do geometry without doing any solving. So this is kind of like doing a degen geom or a try. You can tell it to ignore wakes. All the options are here. You can even plug in no vortex, turn on or off the leading edge suction, or you can do a rotor analysis. Now this is different than doing something akin to a like a full unsteady rotating blade type thing. This takes your entire geometry and cranks it around the x-axis and spins it, the whole thing. So it's just rotor RPM. So if you have a prop sitting centered on the x-axis and you don't want to run it unsteady, you just give it rotor and an RPM, it will run it basically using the regular old VLM methods, but it's turning it each time. So it's a little bit different than trying to run the unsteady case. So one of the things that you'll find can be just a little bit aggravating is that you don't see dash unsteady in here anywhere. But that's one of the things that you call to do an unsteady run. And in fact, if you bring up something like OpenVSP and let's see if I have some of my VSP demos here. Well, anyway, so let's say for this test aircraft, we've got it all set up and we wanted to run VSPRO, and let's just hit launch solver. I don't really want it to do that. I'm going to kill it. But what I want to point out here is this first line.
We can only see part of your screen.
You can only see part of it.
Oh, never mind, you're fine. Sorry.
Okay. Did it come back then?
It was my problem.
Oh, that's okay. So this first line here, where you can see the path and everything else, it kind of stretches all the way over here. That you can copy and paste into the command prompt, and that's where you can get, this big chunk. So you can tell it, OMP 8 unsteady and make it run unsteady. So this is handy when you don't want to use the default application for unsteady cases that are available to you, something like, choosing rotating blades. That will automatically call unsteady, set up the groups file, set up the rotor files. All that stuff is done through the GUI. But that's not the only thing that VSP Aero is capable of. So, for example, if I bring my notepad editor up, I'm not sure if I still have the example file in here. It would be kind of neat if I did. Pity. Anyway, if you set up an unsteady case, namely for something like these time steps, number of time steps, you're calling it and giving it unsteady groups. Down here in this input file, you can also put actuator disks in here. And because some folks asked about some demonstrations of, say, the dynamics and some other operating modes, I'll get into that just a touch. And I've got some videos pre-saved to show you what the solution looks like with these options turned on. In a case like that, where you want to run kind of these, the stuff that you can't really get to in the GUI, you have to set it up through these input files, but you can do it, and it's relatively simple to do. So, for example, in dropped pod case, which we can take a quick look at in a moment, you'll see that the structure of the groups file is such that you give it either a fixed group or you just name it whatever, tell it however many groups you have, how many components are in here, and you can find out what components are what by creating a degen-geom file and then loading up in the viewer, and that will tell you what component belongs to what. So you have geometry as fixed, that's either 0 for false, 1 for true. Same thing for rotor. And the thing that I found out recently from talking to Dave is that geometry dynamic actually has 4 options. It's false, it's dynamic, and you can prescribe the motion here. You can give it periodic, which is dynamic equals 2, or you can do full dynamics, which is 3. And so that's where some of this stuff where your mass and your moments of inertia and everything start coming into play, and it can make some interesting things. So in this case, you can see I've given it acceleration of negative g in feet per second squared, and then same thing for down here. I've made extra stuff that tells it that it's fully dynamic, and so we've got a wing, and in this case, 2 pods that are allowed to just free fall and use their aerodynamic properties to iterate on where they are in space. So it's kind of a neat demonstration. So I guess in that vein, I've kind of talked a little bit about how you would set up the inputs for that. There's this angle max value that gets read into periodic motion with dynamic equals 2, where you can give it the angle rate and the angle max, where it will oscillate back and forth between those according to the described velocity. And so I think, are my videos in here or are they somewhere else? I think, yeah, some of them are in here. So let's come down and I'll see if I can't play some of these MP4 videos and show you a few results. So this one is kind of fun. So this is an example of, say, what happens when you put actuator disks in front of 2 bodies that are fully dynamic. So I've got a tail back here and a wing, and originally, if I crank up the playback on this to go much faster, let's take this up to like 3x, I think is what works reasonably well. So you see it kind of pitches down because it's getting started. The wakes haven't really blown over the tail. But as it gets further and further developed, it starts to pitch itself up, and the whole thing tries to take off. And I haven't prescribed any of this. This is just how the system is behaving all by itself. So you can see that the blowing starts to get a little stronger as the angle of attack increases. Like, it does some wild stuff. And what was kind of surprising is that the actuator disks that I attached to the wing in, say, OpenVSP carried through, like it's following the wing. So it's kind of neat that the actuator disks maintain their position relative to this lifting surface. So that was one example where I both prescribed actuator disks in a fully dynamic simulation and gave it wakes and a tail and let this thing just kind of fly through space and see what happens. Another one here will run some lifting rotors, and again, try and speed this up so that it's not so slow to watch. But you can watch how, as the wakes develop from the lifting surface and from these lifting rotors, that they all start to interact. So you can see this kind of getting pulled down and pulled in, the wakes back here getting ingested and tossed together with these pushing rotors. And some of these others are just kind of out here doing their own thing. But, there's not enough, thrust necessarily to keep this entire body aloft. So you can see that these wakes are starting to kind of nest up on themselves, and they're not getting out of the way and trying to lift this thing off the ground yet, partially because these rotating bodies are rotors and they're not allowed to be fully dynamic at this point. And so another one would be this periodic motion. And because I prescribed the origin vector for these components, or this group, to be about the nose or the leading edge center of this wing, the whole system is rotating about that. But if you wanted, you could, of course, set it at the center of gravity of these two. And again, you get this oscillatory motion, which is handy because you'll find a lot of example cases in things like overflow or other CFD codes to where it uses periodic motion to try and see if it can accurately and repeatably predict, say, a stall angle. So being able to control periodic motion gives you something to compare to, and runs the dynamic cases for you like that. And then the final one that I'll show here is dropped pod. And so as you can see, the wing is fixed, it's doing its thing, but these two are individual components. And watch what happens. We said that body geometries, at least from a degenerate sense, don't have wakes and don't contribute to lift or drag, but they do contribute to moment. And that's kind of what's happening here, is that this thing has its moments of inertias and stuff set up kind of poorly, that the tail isn't doing a good enough job of keeping this thing straight, and the time step is too big, and it winds itself up and just kind of tosses itself into oblivion and then returns a not a number because the run fails. But it's still kind of cool to watch, to see that, VSP Aero has this capability to do 6 DOF, unsteady, effectively free dynamics or even prescribed motion. Like, it's awesome to see how far VSP Aero has come, even in the last year or two, that we can run these kinds of simulations. For anyone that's interested, I made all these videos very simply using the FFmpeg download, and where you can go in the viewer, you click on save as and then movie. So there is a small bug about where the file paths all go, but if you run just an unnamed new OpenVSP geometry and then get the VSP Aero analysis from that and run it unsteady or whatever, you can then go in and then save the movie, and it will write out all the PNGs. It'll build the movie for you. And that's how I made all of these. So if you need an interesting demonstration or just something for fun, that's how it's accomplished right now. So those are just a few examples of some of the dynamic body motion that's capable in VSP Aero right now. And so hopefully that was a sufficient demonstration for everyone there that wanted one. So let's see. Yeah, we talked about VSP Aero from the command line, and the advanced dynamics. I know it's 4 o'clock, but Rob, how do you feel about going just a little longer, or do you need to head out, bud?
Well, I mean, I can hang out for a bit.
Okay. I'd say, for the purposes of at least trying to address some of these tutorials, particularly since we're recording it, and we'll try and break them out into individual demos, I'll just keep on going. So one of them is asking for a demo advanced links, which I've got some fun little things that we can do with that. So let's see. Advanced linking. Where is that? I'm going to go to some of my my VSPU demos. Nope. Down here. Yeah, so this is one that I like to use as kind of a very simple example of where linking can come into play using things like hinges. And I think hinges were specifically called out for doing things like
In
this.
particular for this, did Eric Olson do a talk last year that should be recorded?
Um, his stuff when he was dealing with Horde.
No, his high lift stuff.
Well, yeah, okay, yeah. So I don't know if he got into the details of how he wrote the advanced links for this one in particular, but Rob's right. There is a 2020 workshop presentation that Eric Olson did regarding deployable high lift surfaces. Let's see. I'm looking at the schedule now. Where was that?
So definitely
Uh,
encourage you to go back and watch his talk as a starting point.
yeah, definitely. Was that last year?
I don't know.
Gosh, I, I don't know. Now I'm not seeing it. But anyhow, so this isn't necessarily advanced links, and there are things that you can do, but you'll notice that all of these are linked in rotate. So if I come to my user parameters, I've made one single parameter called a hinge fraction, and I've linked that to every single one of these nested. So all of these hinges are attached to the parent and so on and so on. And you can deploy the entire system as effectively a fraction from 0 to 1. So when you're talking about putting together linkages or complex deployable kinematics, yes, you can do that. It's just a matter of setting it up in a way that is that makes sense. And so there's that, and then there's also heavens. Let's go back to my VSP path, and I believe it's here. Yeah, so this is one I've always tried to get working, and it's another one of these stupid VSP tricks. Don't ever try and do this because it really doesn't work that great. But you'll notice that I've put together effectively a 4-bar linkage, and because you've got components that are going out and touching each other and coming out and trying to keep these tips in the same location, in theory, you can write the equations so that it will point a vector to these places, and it kind of sorts out. And yeah, I think I may have actually just done this with linear links too, but if you play around with this and you go slow enough, it will try and run itself as a linkage. So you can see that I'm not, there we go. Let's give it some extra. So I can make this thing kind of move around, but you'll see that the tips don't really stay together the way that they need to. And it's just one of these weird examples that no, you should really never do it. And in practice, where would you ever use it? But it's an interesting thing that you can do with VSP that yes, there's certainly a more clever way of putting these points together and making a mechanism. But it's doable. So hopefully that gives a bit of an idea about using links in kind of interesting and novel ways. And advanced links, it's just math with semicolons, really. You add some variables. We've given demonstrations, one of which is recorded last year about parameter links, where Rob goes into how to drag and drop parameters in there and how to write it. So you can make it, for whatever reason, you can make diameter a cosine function of some user parameter or something else, or you can make your twist and your span linked in some weird way. But encourage you to go back and watch some of the videos that we've done in the past about this, rather than beat it to death in this one. I really don't think that we have time to go into a start to finish powered VSP Aero run for stability and control. Know that if you want to do a powered case, say with actuator discs, you can do PQ and R unsteady analysis and take a look at it. You can set your control surfaces as deflected, and then go in and post process those derivatives and see what you get. So we've talked a bit this week about how VSP Aero is not going to trim the aircraft for you. You kind of have to iterate around on that and work on it. There's work in progress toward that end, but VSP Aero won't do it for you right now. But what it can do is give you small perturbations, and because it's effectively a linear code, you can extrapolate to some small degree, the control surface effectiveness based on small deflections. And those are also documented in other workshop presentations too. As far as Rob, we talked about this a little bit. Do you want to mention at all some of your thoughts about trying to use VSP Aero or other methods for transonic?
Well, I'll just say that by and large, VSP Aero is based on linearized potential theory, and that breaks at transonic. So, from that standpoint, it's a bad idea, and you should not use VSP Aero to do transonic analysis. That said, if you're looking at designing an aircraft and you're using some known good supercritical or transonic airfoils, and you're looking to design the lift distribution and get a decent drag polar and have a good configuration, I'd say that an airplane that has a good lift distribution transonically probably also has a good lift distribution at a slightly lower Mach number. And so what I would encourage you to do is you're going to need to be an experienced aerodynamicist for this. I'm not saying this is beginner level stuff, but you could certainly look at using the panel code and even the VLM to do things like twist your wing, develop your camber distribution for your supercritical airfoils, and work on your planform design and really design things well at something below that critical Mach number, below where the transonic effects are really going to dominate. And an airplane that's well behaved at a slightly lower Mach number will have a better chance of being well behaved as you increase that Mach number. So we won't capture those higher Mach number effects, and you're going to need something like CART 3D or Navier-Stokes CFD in order to capture all that. But from a standpoint of lofting the wing and designing the twist and getting the lift distribution right and having a stable airplane and really doing your configuration aero design work, you can probably do that design work at a slightly lower Mach number and get yourself very close to that ballpark. So, yeah, I'd say don't use VSP Aero transonically.
Alrighty. And I happen to have this, the cutout mesh available for this, and I hadn't really planned on doing it, but we've got just a couple of minutes here that I think it is easy enough to demo at least how you'd get started going about this type of process. But someone has asked, can we show how to replicate wings using Colfan foils? And I think they might have edited their response or something, but it was kind of a request of a quasi-fit model with wings instead of fuselage bodies. So, sure, why not? Let's back the sweep off, and, just because I happen to know, let's put this, 0.7, bring the root chord back to something like, 2.6. It's not exact, but we can play around with it. And then let's set the taper ratio. And then crank the span out a little bit. Okay, so let's just pretend, for the sake of argument, that we are trying to match one of these, and I'll try and set, say, the airfoil right about there so we don't have a whole lot of fuss to deal with. And it looks like I need to give this just a little bit. Nope, that's too much. 2.5. That's a little bit more like it. Okay. So not exactly in the place that it needs to be. But let's go ahead and see what we can do about this. So we're going to go into model, and we're going to go into fit model. I'm going to try and rotate this around. And again, we're going to pick points, and I'm going to try and select all of these just on this airfoil. Get all these points for us. Say OK. And then because I know that we want to set it to, say, any U and fix U in this case, because it's only a 6.666 should be. Now let's add target. Now what just happened there? Oh, I know what happened. Got to delete all targets. I picked the wrong geometry. Okay, so be careful what you select in here. Let's try that again. My apologies. All right, now we're going to pick our wing that's all the way down in the bottom again, 0.666, add target. There we go. So it's kind of attaching just on the other side of where it really needs to be. And I should have really put that at like 0.6667, and that would have been more appropriate for this cross section. So what I'm going to do instead is nudge it just a little bit. And, maybe we don't really have to get this to match out just the way we want. But for the variables, we can come here to our wing and our airfoil, come out to section 1, and let's say, as was requested, we can use like a clash state transformation and do something like this. Or even, let's just see what happens if we use one of these. So let's make it a little bit easier on ourselves and use a Kármán-Trefetz. Drop in epsilon, kappa, tau, and let's go to the section and let it iterate on dihedral and twist. And, maybe that'll help it a little bit. But again, a well-posed problem, 45 degrees of freedom, 220 conditions. So let's watch what happens. It might not like me at all, and it might just throw everything out the window. But hopefully, it doesn't do awful, right? So it's getting something.
Brandon, while that runs, let me just interject. Just because you have degrees of freedom less than conditions doesn't mean it's a well-posed problem.
Fair point.
An important thing to watch out for, looks like you need a span in here too. An important thing to watch out for is that the variables you're adding are not redundant. When you add parameters, don't add two variables that could have the same net effect on the shape. Because if you do, what'll happen is the optimizer won't know how to achieve that given goal. And so it'll end up just sort of going off into la land of trying to compete those two variables against each other. I see this most often with skinning. If you imagine one section of fuselage and you have strength on both sides, and there's sort of an infinite number of strengths that are give very, very similar answers. And so through that, you don't want to, you just don't want to go down that path. So well posed, certainly degrees of freedom and number of conditions is important, but then you want to be careful when you select your parms that they're not redundant. It looks like you might need to thicken the trailing edge, Brandon, and also give it some sweep control to align the leading edge. The other thing I'll say is Dave Kinney answered the question about transonic arrow in the conference's IO. So if the person who asked that is watching, I'll read the answer. Dave said that lift is usually not horrible at transonic speeds. Drag will be problematic unless you know what you're doing. Emphasis on no. VLM is more likely to be right for the wrong reasons as opposed to the panel method. So, and I think those are all very reasonable, very true things. That lift with the VLM method at transonic speeds is probably better than it has any right to be. So,
yeah.
Back to you, Brendan.
Yep, and all really good points. And this is kind of the danger here, right? Of using, say, a CST airfoil and not setting things up the way that you really should have. So you can see here that some of these targets, because to be fair, the distance, I can search UW and now, aha, that point needs to be up on this point. And some of these others, they're snapping as close as they can. But remember, we told them they were free in W, so it's just going to go to the closest point it can find. It doesn't really care that this is over here. So it needs to be set up in such a way that the points that we give it are in an appropriate location to where it can try and minimize without, trying to target the wrong point on the curve, which is what happened here. But
I would approach this a little bit of a different way, Brandon. When I try and match a wing with fit model, I always try and match plan form first. Um, I ignore the upper and lower surface of the wing.
Yeah.
In fact, I'll
Yeah.
try and go in and only pick out the leading edge point and trailing edge point of a section, and I'll do my fit model using the leading edge and trailing edge point to get the plan form as well as the twist and dehedral as correct as I can. I'll then come in and I'll probably add a simple airfoil, but I'll only adjust the thickness to chord, and I'll just pick a few points on the top surface to get the T over C right. I'll then look at the trailing edge, and if it's a thick, blunt trailing edge, then I'll go to the modify tab and I'll allow it to just adjust the trailing edge thickness to match. And now you're left with just sort of controlling the camber overall, and in this case, a lot of aft camber. But the important thing is that if you go through this process, you can do a better job of making sure that the points are not associated with the opposite side of the geometry, and you're only sort of controlling things as the complexity grows. So that's sort of my personal way of approaching wings. You're absolutely right. If you just steps 10 feet back and grab 1,000 points on the surface of the wing and you add default wing and you hit fit, it's never going to work. So
Yeah.
um, what I like to say about fit model is it's really not that much better. It's not that much better than if you were just moving the sliders by hand. And and I mean that in the way that it's doing the exact same thing, right? The only difference is it can move the sliders much faster than you can, and it's doing a least squares optimization, so it can find a
Mhm.
truly optimal setting of the sliders. But it's even though it can do it faster and optimally, it's no better at it than you are. So, and what I mean is, um, approach the problem using fit model the same way you would do it if you were adjusting the sliders manually. Just use fit model for that final adjustment. And so if you're doing a wing and I was doing it manually, I wouldn't start by trying to match the details of the airfoil at the beginning.
Right.
I would start by trying to get the position right. I would literally start with only adjusting the leading edge root of the wing. And once I had the position right, then I would adjust the leading edge tip. And then I would get the chord distribution. And I just do sort of one thing at a time, the way I would do it manually, except I would use Fit Model to help me along in that process. And once I had a parameter adjusted, take it out. Don't adjust it again. Once you've positioned the wing in 3D space, don't let it move. Don't let it free up again. And that's how I'd go through it.
Agreed. And that's absolutely the way that anybody listening, anybody watching the recordings, to do an actual fit of a plan form, start with the biggest stuff first and move on from there. So, the kind of disclaimer on the stuff that we showed there just a moment ago is that that would be an approach to how you can try and get the upper and lower surfaces after you have done all that other stuff. So, use with caution. And in most cases, I would recommend not even going with something like a CST or a carbon treffids foil for trying to do stuff like this. If you know or have a pretty darn good idea of what kind of airfoil it is anyway, either from the UIUC database or just from looking at it, use that airfoil. And
Well,
you're going
the
to have a better idea of how to fit it.
the Carmen Trefitz is not really there for real people to use.
Right.
The reason Carmen Trefitz is there is because there's a two-dimensional analytical solution for it. So
Right.
the Carmen Trefitz airfoil is really only there for use in validation exercises. That if you want to have your code and you want to generate a KT airfoil and write it out and do a 2D validation, that's why it's there. No real airplanes have a Carmen Trefitz airfoil. So don't even
Yeah.
take that out. Using the CST is fine. But I would definitely, if you know it's got a NACA 6-digit airfoil or something like that, then obviously use that as the parameterization. If it's something else, using CST is fine. But what I would start with, this is a little bit nuanced, but I would start with a simple NACA airfoil. I would start with an analytical airfoil. And again, I would dial in the thickness to chord first. I would then dial in the trailing edge bluntness. I would then, try and dial in some camber. And I would do that on a regular airfoil. And if the fit was still not sufficient, all of these airfoils have a button that will convert it to the best fit of a CST. And so what you can do is you first go through a process of getting say the 5-digit modified airfoil that best represents the data. And once you've once you come to your wit's end there, once you've gotten the best you can do, you then hit one button, and now the initial guess for the CST picks up where you left off. And so now, again, you can avoid that problem of associating points with the wrong side of the geometry and trying to get some of those things wrong by converting that complicated airfoil to a CST to start with. And that'll get you a lot better ability to then go in and use the CST to just sort of nuance the details you couldn't get otherwise.
Yep, all great points, and appreciate the additions there, Rob, because that's good guidance and good practice for everybody that's listening in. So heed the master. There's another request for tutorials and stuff here. It's how can you import things into MATLAB for further analysis. There are demonstrations, I believe a recorded presentation from last year about how to set up the MATLAB API and some discussions about that. So we won't go back and do that again. And of course, there's always like parsing all of the output files that are available. So if you need the polar data, or if you just need information about the geometry, you can parse any type of output from an analysis that's written out. So you can do that as well.
But if you've connected through the API, you don't need to,
right,
because the API will give you all that stuff in memory. Yeah, the right answers, if you're using MATLAB and you want to work closely with VSP and not just sort of do it through files, watch, I think it was either Justin or Nick Brake's presentation last year on compiling the API, and there's a presentation last year on setting up MATLAB and compiling the API. That's the ultimate answer. The other thing that we do have tight coupling with MATLAB is the dgen geom analysis will actually write out an M file. And so then you can just run that M file in MATLAB and it'll load just a tremendous amount of information into memory. And so if you look in the VSP distribution, in the examples scripts, there's a MATLAB script in there that will help you visualize the contents of a dgen geom file. But that's the other thing that we have that really supports MATLAB directly, is the ability to write a dgen geom file to that. And I'm not sure if there's a video recording, but we've done presentations on what dgen geom is all about at several of the past workshops, probably one of the recordings. So you might go watch that and then try loading that M file into MATLAB and see what you've got.
Yep. And for the viewers, I showed where in the MATLAB folder those examples are, and for anyone that cares to look, the demonstration about the OpenVSP API in both MATLAB and Python is here on the 2020 workshop page down here, about fourth or fifth from the bottom. So that's right there. All right. Well, I mean, it's almost 4:30. I know we went about a half an hour long, and we kind of stretched a little bit, but I feel like we really covered a lot of material this year, even though it felt, at least as far as the schedule was concerned, that we didn't quite have enough to flesh everything out. But man, we certainly covered a lot of material. So I hope everybody online enjoyed the workshop, had a good experience, and we appreciate all your feedback and answering the polls, posting your questions, and letting us know what it is that you wanted to hear about. Hopefully we did a good job of passing that information along. As always, thanks everybody for attending the workshop and for participating. And we appreciate your time. We appreciate your feedback. So by all means, let us know how we did. Go check out the ground school. Send a contact form to us. And, thanks to Rob. He stepped in a big way here recently and volunteered for quite a bit of this content when he really didn't have to. So I really appreciate his efforts in making this yet another really successful workshop where we were able to reach quite a few people from all over the world. So thanks to everyone for that.
Thanks, Brandon. I think the last thing I'll say, there have been some really great suggestions in the conferences IO. We've got about a dozen things that have been captured in requests. Many of them I understand what people are asking for, but some of them I don't. I'll admit I'm not entirely sure what some of them mean, and some of them are complicated. So I'm going to do my best here. Unfortunately, the survey form didn't capture who made the request, so I can't follow up back with you. So if you've got something in there that's important and is preventing you from getting work done, follow up either on the Google group or send me an email or do an issue report on GitHub, and we can try and do it, or at least try and understand that I can either give you an alternative or maybe try and find a way to implement it. But we're going to capture this list, and I'll do the best I can. But I don't have a way to follow up with you, and I don't know who made the requests.
Yeah. So that anybody that needs to be put in contact, I've had my email address on many of the presentations, or you can go to the 2021 workshop page and click the link to send me an email, and I'll make sure that that information is passed along, and hopefully we'll get those requests put in, and we won't lose any of this. But all of the stuff from the live chat and from the conferences IO is going to be exported and saved so that we have a record of all of these things that were requested and everything that people were asking about and the live demos and things, because that helps us get an idea for what it is that people are after and what it is that they need help with, and that's good information for us and for me working on the OpenVSP Ground School to know what is it that some people might need more help with than perhaps something that's a bit more rudimentary. So thank you again to everybody, and to Rob, to all of our presenters for giving their time so generously and giving us updates on their work. So I don't really have much else to say aside from thank you once again. And Rob, if you have any other closing remarks, I think we've said our piece and are ready to go ahead and close the workshop for this year.
Thanks, Brandon. I'm good. I need to go get some lunch.
Yeah. Yeah. All right. Well, thank you again to everyone online, and we hope you all stay safe and healthy, especially with the way things are in the world now. And we wish you all the best, and we appreciate your time and your participation. So thanks, everybody, and we'll see you next time.